weiter eins, zwei. Test, test, test. Okay, hello everyone. Welcome to the JuliaHab mini symposium and the JuliaCon 2026. The JuliaHab, just to introduce ourselves a bit, is like an interest group in the HEP Software Foundation, and I'm a convener of this group, and we organize this mini symposium for you, showing you a bit how Julia is used in high energy physics, hadron physics, and other related fields. Our first speaker of today is Dhruv. I will not try to pronounce your full name.
That's fine.
And he will talk about a composable Julia stack for hadron physics. So take it away, Dhruv.
Okay, thanks for the introduction. So I am Dhruvanshu Parmar. I am a PhD student in Misha's group at Ruhr University Bochum. And today I will be talking about, in a way, how a stack can be is used for of different packages that can be used for studying hadron physics. So the overall question that we would like to answer is, once you start with an optimized parameter set, how you can transfer it to a normalized PDF, which can be used to describe a multi-particle event. I think there is a lot of feedback, right? Okay. Am I audible? Okay. All right. Sorry for the feedbacks then. Okay, so without further ado, I will start. And this is a roadmap, which in terms of gaming terminology, we call it a playthrough through different packages that I will demonstrate. So we first start with a parameter bookkeeping system through build constructors for fit control. Then you play along with different probability distributions and parameter space domain through the packages which are listed there. Then you can also play with amplitude calculations and particle frames for different processes. And in the end, you have a framework to process all these amplitude models in the end. The feedback. Yes, please. Hello? Bit better. Something is better than nothing. All right. Um, so yes, I will be going through some of these packages one by one and briefly describe its functionality. So first, starting with compact parameter bookkeeping for outside physics model for parameters. So it's a tool which is used to store parameter metadata like the names, starting values, bounds, and uncertainties. So the way this works is that it wraps a struct type constructor as shown here, which can take abstract parameters as inputs, and it defines certain fields to describe those parameters. And then you have a method called build model. Oopsie. A method called build model, which basically takes this constructor as input and the parameters. And what it does is that it assigns the values to the parameters mu and sigma here, for example, in such a way that depending on how the parameter is described, it either takes the value which is already described in the constructor, and otherwise it will try to find a matching name of that particular name of the parameter in the pairs array to find the value. An example is shown here where two different types of parameters are described. So for mu parameter, as you see, you have values mentioned, the boundaries for this parameter, uncertainty, and the state. The state here basically indicates whether the parameter is fixed or not. So false means it is not fixed, and true means it is fixed. And so you say that this parameter sigma is fixed here. And so I just pass this to build model, and you can see that because sigma is fixed, no matter what I pass, it will still accept. So this paradigm can be shifted to have a mixture model, which could be like a combination of different constructors of different distributions to get a construct of the mixture. And in addition to that, there is also functionality called fix exclamation, which what it does is that it basically fixes parameters on the fly while doing some fitting algorithm, let's say. Where an example is shown here where you had 5 parameters at the start, and then you do fix not for the constructor, and you have only 3 parameters which are free now. All right. Next, we come to distributions. And first of all, I would like to thank contributors for distributions.jl, which leads to the foundations for distributions HEP, which basically, as the name suggests, it's a collection of distributions specifically for HEP-based applications. So you have an example shown here for crystal balls, bifurcated Gaussian, and hyperbolic secant. In addition to that, it also has features to get PDF and CDF and all the other distribution-related properties as inherited from the distributions.jl. In addition, you also have a method called extended mixture model, which instead of taking fractions as input to combine different models or different distributions, you can also pass non-zero weights, which are like yields, which are generally you can get from while you are doing an extended negative likelihood fit while doing the fitting. And this can be passed to get the combined model. Strictly speaking, for distributions HEP, you have distributions for functions which have a closed analytical form. What if you don't have a closed analytic form? In that case, you come to numerical distributions, where basically, as the name suggests, you can pass on any unnormalized distribution to it, and then you can have it has a way to normalize it via integration by default by quad GK to get the corresponding PDF. Examples are shown onto the right, and the code block is shown at the top. In addition to that, numerical distributions also has a feature called FFT convolve, which basically carries out a bin type convolution via fast Fourier transforms. If you have two specific distributions, D1 and D2 mentioned here, which have a finite support. And the corresponding example is shown here, where you have this D1 distribution, which is an exponential -4, x power -4, and B, which is this dotted distribution, which is a Cauchy-like, and the combined line, which is a dark blue color, which is a convolution of both of them. Next, once you have these distributions defined, you also would like to have a way to generate a parameter space, or rather, I should say, phase space corresponding to your physics processes. And for this, you have Rambo and Dite, no pun intended on the name. So it basically does is that it basically maps the 4 vectors for the 4 vectors for the particles from the involved in the process to a hypercube of dimension 3n minus 4, where n here is basically the number of particles you see in the final as the final state particles. As for the example shown here, you have this 3 as the final state particles, so n would be 3 here. So it has a space generator which generates a phase space, and then you can just use ren to generate any random point in this phase space which corresponds to a particle associated to this particular process. And one thing to mention, if you have massless particles, then you have a flat phase space, which means it is unweighted. But if it is not the case, then you assign some certain weights, which are like Jacobian type weights, which are assigned to a flat phase space. Then comes hadronic line sets, which is specifically aiming towards calculating amplitudes. So distributions are kept separately, and then you have amplitudes separately handled by this package, where you have a line set which is complex in structure, and you can basically get observable intensity by calculating a modulus or an amplitude for it through some flex functions, which are also available in the package. And then you normalize it using numerical distributions. As mentioned, you have different line sets available for Bright-Wigner, multi-channel Bright-Wigner, and Flatte. They are plotted here as shown. And then you also have form factors contributions through Blatt-Weisskopf, which are used to calculate this particular line sets. As seen in the plot here, you see a single Bright-Wigner, which is being plotted along with a 2-channel Bright-Wigner, and then you see that although they almost peak very close to each other, but there is a slight gap depending on the different processes which are considered for the 2-channel Bright-Wigner. The star indicates that it could be a new particle, but needs more steps to verify. All right. Then there is also a package which takes care about as an interface to handle 4 vectors. So at first you have Lorentz vector base, which creates a customized vector space in a customized coordinate system as defined in the package. As shown here, you can have a 4 vector defined following a Cartesian coordinate system x, y, z, and time. And once you have defined one of them, you can just call each of these components individually, and you do not have to define others individually, because they come along with it as you define the system. In addition to that, you also have a shared interface to get different kinematic outputs like masses, PT, eta, rapidity, and all those things. Then you have 4 vectors, where what 4 vectors is doing is that it creates an immutable Julia vector, which is a 4 vector, with like a 4-element vector as shown here. And it comes with this, in addition, some physics transformations like rotations and boost, and other Lorentz transformations that can be carried out. And here are just showing some common output for different code block which can be run through 4-vector package. Then comes instructional decay trees, where the idea is that if you have, let's say, a particular process that you are studying, for which you need to calculate helicity amplitudes, for which you need to go through one rest-frame to another rest-frame, depending on the resonance that you are considering. In that case, you would like to have this information easily available instead of storing it in like in some black box inside a matrix. So what instructional decay trees do is that it creates a program-type interface where this information can be stored. So an example is shown here for the decay A going to B plus C plus D, where you have a sub-decay for A going to B plus C, which is shown by this blue frame. So it basically tells you that it first go to the helicity frame involving the particles A, B, and C, and then you can have a functionality to measure some physical quantities like azimuthal angle or the theta angle for it. All of this can be calculated, and then you can take this particular object as the input and then pass on to another rest frame, like for example here, going to particle B and C specifically, and also do the same tasks again. So all of this information is programmable, and it can be easily defined by the user, and you can see what's going on there. Then I come to the last few parts about processing these models, starting with three-body decays. So in three-body decays, what is being shown is that you have a process going like A going to be B, C, D. And then you want to look into some specific resonance structures, which can be obtained by combination of two of them, like particle two combinations. And all of this can be taken into account as long as you have three final state particles. It also takes into account spin couplings, parity, as well as Wigner rotations. And as you can see, a generated plot from this particular package involves a Dalitz plot here, showing for the process, if I am not mistaken, it's lambda B0 going to J psi PK. Yes, I think so. I could be wrong there, but you just have some three-body process, and where in the Dalitz plot, you. Okay. Can I just quickly browse through? Okay. Where the bands are showing different resonances, which could be observed in each of these two particle combinations, which are shown in the plot. And this particular topology can be extended to multi-particle decays through cascade decays.gl, where you need to be very careful about how you are assigning the particles, because it also takes into account the two particle combinations and transfer it from one particular chain to another chain, as shown by the diagram. And then you can do similar task where you define the topology, get the kinematic information, get helicities and amplitude values, and then you can also carry out further Wigner rotations. This is controlled by cascade decays. So this brings me to the end. So I showed you a playthrough to different packages. Each of them links are shown given here for you to go along and explore it yourself. So the idea is that you can start at any particular step, like some of them are listed here, that if you want to go for modeling, you can start with build constructors. If you want to go play with PDFs, you start with distribution SAP or numerical distributions. And if you want to go for decay amplitudes, you can start with three-body decays, and for more complicated decays, goes to cascade decays. That's all. Thanks.
So thank you very much.
Yeah. You've got many different packages for doing each of the specific things. You've got many different packages for doing each of the specific things. How do you make sure that everything keeps working coherently? Because that's a lot of packages that will depend on one another. Did you comment on that?
Well, of course, it means that someone has to keep on maintaining each of these packages, and also which I specifically have seen these issues myself, that as you mentioned that this could have certain dependencies, and Julia is very sensitive when it comes to dependencies. So one way to handle it could be that these are modern times. You can have certain AI agents which can go through, have timely commits, which can go through a cleaning for the package and then make modifications as you ask for them. And as like I said, you can have a team which can take care of it, of timely updates, and ensure that everything is coherent. Basically, you have to work hard to maintain it, which is not an easy task, I know.
Okay, thank you, Driff, again. And now I'm thrilled to introduce Sam Skipsey. He will talk about experiences of Julia versus other languages as an educational target for undergrad physics. So take it away, please.
Am I coming through on the? It's not amplified. I might need. Oh, am I? Now I am. Right, okay. So yes, I do have a stopwatch on. I've used 30 seconds to work out if my microphone is working. So hopefully we will all keep to time. So yes, I gave rather a rod for my own back by deciding on this title and then discovering I have 15 minutes, because I asked for 15 minutes, and then discovering I have 10 minutes. So we will see how we go. So firstly, if you want to read about any of the things that I'm going to walk through very quickly, some things that you'll be able to see on this slide, there are references. I'm exerting from my own chapter in teaching programming across disciplines. There's also some references from other chapters. I recommend Feli and Herman's work on gradual programming in general, and some work on teaching languages in general. And in general, this talk is based on experiences helping with various Julia workshops, and also running Julia workshops at the University of Glasgow, and trying to get Julia to be a teaching language at Glasgow in physics, which didn't quite work, but we'll talk about that. So what I want to talk a bit about first, though, is many of you probably haven't taught programming to undergraduates recently. Let's talk about some principles of teaching programming to non-CS students. And I'm going to go through these one by one. So firstly, there's no such thing as an intuitive programming language. People who say that are idiots and need to think about how people think, right? What is intuitive is what is familiar. So what may be intuitive to one cohort of people you're teaching might not be intuitive to others. And so when we want to introduce a language gently to a particular cohort, we want to pick a language whose syntax is similar to the way in which they're used to actually expressing concepts. However, and contrasting with this, a more recent argument in teaching to non-CS students is that non-CS students don't really want to learn to program. They don't just want to say, I want to learn to program because they want to learn to program. They want to learn to program so they can accomplish tasks in the actual domain in which they are learning. So physicists want to learn to program to do physics. Engineers want to learn to program to do engineering, right? Only CS students want to learn to program because they want to develop Haskell in the future. So it's really important to lead, rather than teaching syntax from the ground up, lead with useful examples that actually show how you can apply to the skill in particular. And this is where having intuitive languages helps. And as part of this, we also need to develop syntax and concepts as gradually as possible. A lot of programming languages have this problem that we throw an awful lot of syntax at people at the very beginning. It overwhelms them. This is true of Python as much as it is of any other language. When you're teaching languages to people new to programming, we need to, in fact, be very careful about this. Feli and Herman actually did some work on Hidi, which I commend to you, her work on this as a gradual programming language for teaching preschoolers, and indeed children at school languages by building up. Eventually you get to Python, but it takes a while to get to Python. You need to build up concepts gradually. And finally, I'm not going to talk too much about this, also there's this problem of setup cost, right? Any tool that needs installation will be incorrectly installed. This includes Python. I have run Python workshops, especially with Windows users, where they've tried installing. There's weirdly two ways you can install Python on Windows, and one of them screws everything else up. And people will invariably choose the one that they shouldn't use. This happens a little bit with Julia. I'm not going to talk about this, but Julia Up actually solves a lot of these problems. It's one of the nice things about having Julia Up. So, as an aside then, a brief history of people teaching and using languages in HEP. I've stolen one of these graphs from Graham. Graham, who's sitting here, gave a talk about Julia as a language for HEP at CHEP in 2024, and he had this timeline, the use of languages in high-energy physics. You'll notice that we all go back to the 1950s. I was trying to produce a timeline of languages taught in physics undergraduates. I could only get back to about 1980 or so with actual with things that were available on the internet. But you can see there's a similar pattern. We have this period where everyone teaches Fortran. There are still, in fact, physics undergraduate courses in the UK, certainly teaching Fortran, modern Fortran now, as a language to undergraduate physicists. The University of York, my alma mater, does, for example, still. And then we had this period where people moved over to C++ a bit, and C because it was cool and performant and everything. We have a brief period where people played around a bit with MATLAB, and I feel that Julia, in many ways, usefully takes over from MATLAB in many ways in terms of its naturalness. And of course, now we have this thing whereby Python, as Python became a massive data science language, Python also takes over the mindshare. Everyone wants to learn Python, so Python just takes over in all of your courses. However, we do see in the last couple of years, in particular, Julia turning up in some universities as an undergraduate teaching language. And there were various reasons for these shifts, right? The technical relevance, as Fortran stagnated in the 1980s, people moved away from it. There's also popularity reasons. But the chicken and egg, the elephant in the room is that at the moment, Julia is not a super popular language. It is not a Python. Very few things are a Python. So I made this graph. Everyone has a favorite way of calculating language popularity. So Advent of Code is an online annual coding competition. There were 24 problems each for the days of Advent up to Christmas Day. There were now 12 because people complained they ruined their Christmas Day solving the hardest problem. And there was a survey of who uses those languages, and people tend to use Advent of Code to learn a new language. So this is actually very biased towards learning languages that are either really popular, or you have a popular language, you want to learn an interesting language. And you'll notice that as a result of this, Haskell actually comes surprisingly far up. Haskell is kind of here. And Julia does chart, but it's a little bit further down. It doesn't really have the mind share. And this is actually quite biased towards, I want to use an interesting language. Rust, of course, does incredibly well on this benchmark because cool, sexy language that people want to learn, right? But we should note that Python also wasn't super popular. Python dates from 1992, right? Python took 15 years to become anywhere near popular. So this isn't something to worry about now. So why is Python popular? Is Python popular because it's an easy language to learn? Of course it's not. I will move the slide after this to keep the time. I'm halfway through my talk already, I know. So this is an example of what I mean by Python not being an intuitive language. So on the left, I have some simple paraxial optics. It's a very simple test where you have a transformation for a lens on a lens matrix, and you can show that lens addition works. Doing this in Python requires you firstly to import NumPy, and then to have a whole bunch of line noise about defs, and people can need to understand what a return is, need to make an array. They try to use the matrix operator. It actually operates element-wise, so you have to understand what this array true means. This is awful for teaching early undergraduate physicists a language. There's so much noise here, they can't see what to do. So if we do this in Julia, this is what it looks like. And this is kind of my point, right? This is about syntax, but it also isn't. It's about what the language cares about. Julia cares about mathematical expression, and therefore it is very easy for us to map concepts that physicists care about. Immediately they can see how they can use the language to do work. And then we can build this up. We can gradually add, in blue, there are concepts being added at each point in time. And we can go all the way, right? Okay, so going back, we can add long-form functions, optional typing. We can add a function that does alternation. We can add return types, and we can go all the way in principle to inspecting the actual compiled code if you want to do high-performance computing concepts. This is relevant to me because my pitch for Julia at Glasgow was at a high-performance language, and we could go all the way to inspecting performance of code. I'm going to skip, for reasons of time, the lab scripts with Pluto demo. The main point I was going to make was that because Pluto has hidden cells, has reactivity, you can put a lot of frameworks that the student can't see that allow them to have easier ways of using a lab and developing things like using unitful and measurements to do analysis. So I'll come to a conclusion then with some feedback from students. So I've introduced students to Julia in various workshops. Positive things students say about Julia. Firstly, interestingly, a lot of them do say it's much easier than Python, or because I've exposed them to C before, this is much, much easier than C. They also quite like the LaTeX-iness of writing expressions. They also, if they've come through Python, they're immediately amazed that you can actually do things that take zero time compared to Python stuff. Negative things, though, and this is the slides I wanted to actually have time to talk about. I do get a bunch of students who say the documentation is hard to read or hard to understand still. And I will note that every so often if someone says, let's make LLMs write the documentation, this is not a solution. If you are saying, use LLMs for documentation, you are saying, I don't care enough about documentation to do it myself. Okay? Generally, when people say, let's use LLMs, what they mean is, I don't want to worry about this. They also get this problem that there's a temptation to say Julia is supported by Jupyter. And what happens then is they try to use some random cloud Jupyter instance over here that isn't Google Colab. And of course, it doesn't support a Julia kernel. And then they get confused. This is a popularity issue. And I think this will get better as Julia becomes more supported. However, more importantly to being allowed to teach Julia, things teaching committees say when you try to pitch Julia to them as a language, and this isn't just me, I've talked to other people who've failed to get Julia accepted. So firstly they say, I haven't heard of this language, stroke it isn't popular, why do we teach Python? Transferable skills are about making people employable in the real world, and everyone uses Python. This is a popularity issue. We also, and I have genuinely heard this, and I think the latter two are motivated reasoning, I've heard both. I read this blog post 6 years ago about how Julia has numerical correctness issues. Now, these issues are resolved, but people still bring it up. And I had a quick look at the packages, and all the packages are v0.x, which is a problem that Rust has as well. This is the curse of semver. This is this problem that if you want to go to from 0.x to 1.x, and you're being strictly semver compatible, it's suddenly you're breaking chains to everyone, and no one wants to do it. This does mean, though, that if people have motivated reasoning to resisting Julia, they can look at this semver, they can see the semver problem, and then say, oh, but this isn't stable. So this is about understanding how people who aren't Julia people think about stuff. I mean, I've also heard people say no need to learn the code because you have ChatGPT, so there's various levels of motivated reasoning you see. So I will finish on this slide then. I do think, and I disagree a little bit with the great Simon Peyton-Jones here, sometimes you do have to compromise on your vision to in fact become popular. So I think, and this was inspired partly by Fonza stepping down post as leader of Pluto.gl development, I think we do need to have more people that care about people seeing Julia as being a fun, friendly language that people can use, and perhaps a little backing away from performance at all costs at this point where we are now. Because we have lots of performance, maybe we can make things more engaging. And I will go to questions, because I have like 2 seconds left for questions.
Thank you very much. I mean, we have time for a quick question, but I need to say we have 12:30, we have a panel discussion on some of these topics where we discuss like what Sam showed it here in a bit deeper manner, maybe. So, but is there any urgent question for now?
I'll also say, while you're going over there were 2 other talks on teaching Julia that you should go to that are at the bottom of this slide.
Not too urgent, so feel free to cut me off. You said you hadn't implemented in a formal module yet, right? Are you planning to, and how would you set assignments?
Yeah, okay, so I did a lot of prep work on a formal module, so essentially there was if you read my chapter in teaching programming, it's free online. I talked a bit about this. We tried to pitch. We had a transformation of a course that taught C that Graham will remember, because Graham used to teach it back in the day. And one of the alternatives was moving to Julia, and I did do a lot of prep work on that, so the module actually kind of technically exists. But it was not approved in favor of moving to Python and NumPy, because this was believed to be, again, transferable skills, etc. I also have a high performance programming thing. I'm very interested in the other talk about a high performance programming course in Julia, because it probably looks like this. I've tended to write workshops instead, because I can get people to go to them. I'm going to shut up and let Graham speak, I think.
Okay. So let's thank Sam again. Thank you very much. And I'm glad to introduce the next speaker. It's Graham Stewart, and he will talk about parallel processing in jet reconstruction. Take it away, Graham.
Okay, thanks, Uwe. Yeah, I'm very happy to talk about work that we've done recently on the jet reconstruction Julia package and finding out how well it works when we do parallel processing. I'm presenting this on behalf of my co-authors Harshit and Mateusz, and particularly I'd like to say that almost all of the work here is due to Harshit, who's our GSOC student this summer, and we're very happy with the progress that he's made, and you'll see by the end of the talk why. Okay, so a little bit about jet reconstruction. So particularly at the LHC, we have a lot of very high energy collisions between protons. The protons smash together, they produce very transient particles, which then break up into other particles, so you never really see the particle that you're interested in, you just see what it actually decays into. And you are, of course, using proxies from the decay products to infer what the properties of the original particles were. So software, in terms of reconstructing an LHC event, is really important for us. Okay? Jets are basically sprays of high-energy particles that come from progenitors like quarks and gluons, and they look a little bit like this when you measure them, at least in a 2D slice inside the detector. You can see many, many tracks which are coming out, and these bars at the end are the measurements of the energy that we make inside the calorimeter. And what we would really like to do is take these energy distributions in the calorimeter, and we want to map that back to what the original particle that caused the jet actually was. Okay, so how do we do this? Well, there's classic ways that this has been done, but serial jet finding is the mainstay of jet reconstruction in high energy physics. And the idea here is that we take the group of particles that we found in the calorimeter, we measure distances between those, and then the two particles which are closest together, we merge those into one particle, and then we do the whole thing again, and we merge the next one, and the next one, and the next one, okay? And in particular for proton-proton collisions, we have two parameters that help us to do that. One is incorporating information about the transverse momentum of the particle. And what that means generally is that we use this P equals -1, which is anti-kT, which means that we tend to merge the jets with the highest amount of momentum first. Turns out that physics-wise, this is actually a good thing to do, but you can pick other p-values as well. And we also have a cone in which we will not merge any particles which are more than the cone distance apart, so you end up with jets inside the cone. And it's an iterative algorithm, but there are some opportunities for parallelism as well. One interesting thing is that to speed up the algorithm when you're using one of these radius-bound reconstructions, what you actually want to do for optimization is you want to split your particles up into little blocks. And what's nice about this is that you only need to care about the nearest neighbor blocks. And this really helps to reduce the computational burden. This is called the tiled approach to jet reconstruction, and that's the one that we most often use at the LHC. Okay, so there's a standard way to do this in C++. It's a package called FastJet. And what it does is it allows the user to define the kind of jets that they want, and then to inject the particles that they're interested in, and lo and behold, out come the jets, and then you can look at various properties of the jets as well. So it's a very simple package to use, and it's become very popular. It's also quite computationally efficient as well, so all of the LHC experiments are happy to use FastJet. Now, we wanted to experiment with Julia and see if Julia could do the same thing. This work that started about 5 years ago. And so we have re-implemented inside of Julia the various sequential jet finding algorithms that are found in FastJet, the popular ones here, supporting both PP collisions and E+E- collisions. And then there's a whole bunch of things that you can do afterwards once you've found the jets, if you're more interested in things like substructure or jet cleaning. But the interface is also pretty familiar. So we have this cluster sequence object, which is what encapsulates the reconstruction information. You basically feed it with your particles, which algorithm would I like to use, the radius, and you can define the strategy if you want, but if you don't, then the package will just pick the best strategy for you, and then you can find the inclusive jets and do all other kinds of manipulation after that. So, great. Just a quick flash to say why we use N2 tiled. This is just a performance comparison on typical LHC events, where you can see that the tiled algorithm is about 3.5 times faster than the plain algorithm. So that's the one that I'll talk about for the rest of the talk. And of course, you know, we're in competition with FastJet, so we have to compare ourselves in speed to that. And the last set of benchmarks that we did on the particular test machine, we're about sort of 25 to 30% faster than FastJet. So very good result for Julia, that we can actually achieve better results than FastJet. Now, of course, this is all done using one core and serially. And that's a little bit embarrassing, because I've noticed that computers these days have more than one core. So we better maybe try and use multiple cores. How would we want to do that? Well, the algorithm itself, although it does have a little bit of parallelization opportunity is not really very suitable to parallelize widely because of various serial parts. So what we want to do is we want to parallelize on events, because after all, I have many different events that I want to process at the LHC. Remember my 30 megahertz. So I have plenty of events and I have plenty of cores. Great, let's parallelize each event onto one core. So we do that in Julia very simply. When we have a loop over different events, we simply use the threading module. We say, okay, just push these out onto lots of threads inside of Julia. And we needed an equivalent thing for FastJet, so we just used OpenMP, which is a very easy way of getting parallelization on this kind of thing. So great, off we go. How does it work? Not very well, it turns out. So although we're definitely still faster than FastJet, up to about 4 cores, then things go horribly wrong. Okay? Whereas FastJet is scaling like really nice, kind of pretty good linear scaling. If you look at the efficiency of FastJet at 64 cores, it's getting 92% of its single core performance multiplied by the number of cores. We're getting 10%. Oh dear, something terribly bad has happened here. So, of course, we need to try and investigate this. So first of all, we think, okay, well, maybe it's a scheduling problem. What could we do about scheduling? So we tried to see whether the default dynamic scheduler would be improved if we changed to the greedy scheduler, which is a little bit better at assigning work to threads when the threads become free, because not every event is the same. Maybe this is causing some problems. So we did that, and actually at low core counts, the greedy scheduler does a little bit better than the default dynamic scheduler. And then something even worse happens at very high thread count. So somehow the dynamic scheduler is now really terrible when you try and run it on 64 cores. So this is not good. All right, there's no simple fix. What do? We need to investigate what's going wrong. So the way in which we profiled this was we attacked it with various standard profiling metrics inside of Julia. One is to just use the Julia profiler and to look at and have flame graphs and look at where the code is spending time. We also used perf because we really wanted to see what was actually happening on the CPU itself, and the various Julia built-ins that we can use to get timing and garbage collection statistics as well. So what's the first thing that we look at? Well, let's try and find out what's going wrong with the scheduler. And we discovered this very interesting thing that basically the greedy scheduler on our problem collapses at about 32 threads. So what's happening is that in terms of garbage collection between 20 and 32 threads, there's not much change. In terms of the actual physics reconstruction, not much change. Oh, look at what happened to the scheduler at 32 threads. It's a disaster. So we kind of overwhelmed the greedy scheduler's ability to schedule work effectively. It was spending so much time looking for the next thread that actually it was able to take any work that it was not able to dispatch the work in a reasonable amount of time. So, okay, that's not so good. Next thing we looked at was garbage control, garbage collection. So the immediate thing you can do is you can just switch garbage collection off, okay? This is not a practical solution to anything, as nobody has very much memory anymore. It's rather expensive, but it does give you some hint as to whether garbage collection is causing your problem. And clearly, garbage collection was causing a bit of the problem, because you can see that the event rate that we get does indeed go up when we switch the garbage collector off, but it doesn't go up by that much. So switching off garbage collection is not saving the world here. So we were now sort of struggling a bit to try and think exactly what it is that's going wrong. So then back to the scheduler. So we decided that we would try and fix the scheduling maybe by building something that's a little bit more akin to OpenMP's dynamic scheduler. We call this chunked atomic, where we just have a very simple distribution of work onto the different threads. Essentially, when a thread runs out of a work block, it then just grabs the next work block from the event queue. And it turns out that this did improve things a bit. So the chunked atomic scheduler is this green line here. So we were both able to reproduce the benefits of the greedy scheduler at low thread counts and maintain the throughput at rather higher thread counts. But this was clearly not the solution to the problem either. So again, this led us to the conclusion it's not scheduling that's going to save us here. So what is the next thing to try? Where are all my CPU cores going? What are they doing? We thought we'll check that nothing bad is happening inside the physics algorithms. So the first thing that we tried was we looked at perf and the various perf metrics like cycles per event, the instructions per cycle, cache misses, blah, 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 all the kind of things that you usually look for in perf. And you can see that the numbers are pretty flat. So there's some degradation in the cache performance as we run on many, many threads, but certainly not enough to explain the performance degradation that we're seeing. So it looked as if there's nothing particularly bad at that level which is going on. Then we dug into the actual physics jet reconstruction work to look at the amount of time that we're spending on the actual physics jet reconstruction. And again, this is almost flat. I mean, this is kind of expected because each event reconstruction is running on one thread. But it was a good verification to check that there was nothing horrible happening inside of the algorithm. So our algorithm is certainly not going wrong when it's running multi-threaded. So this is not the explanation either. Now, then we looked at the garbage collector in a little bit more detail. And the allocation per event does stay flat. So each event is using about the same amount of memory as it uses, whether you're running on one thread or whether you're running on 64 threads. But we looked at the amount of time that the garbage collector was active for versus the amount of time that the physics reconstruction was actually happening. And what we could see was something really bad was happening. So this is the percentage of the wall clock time which is used by the garbage collector. And it goes from being quite small at one thread to being really horribly high at 64 threads. So 80% of the time, we're not doing any physics at all, man. We're just doing garbage collection. So clearly, this was like for us the smoking gun that actually it's to do with allocations and garbage collection, which is the problem. So another way of looking at that is in this plot here. So what's your wall time budget at 64 threads? Well, it's about 18% doing physics, and it's about 82% doing garbage collection. And if you do a sort of quick heuristic calculation, we've managed to turn 64 cores into just about 13 cores, which are actually doing any real work here, which somehow explains the very poor performance that we were getting. Okay. Digging into this a little bit more, we could see that the sweep time actually stays pretty constant inside of the garbage collection. So the time that it's actually freeing up the memory from objects that don't have any references anymore. We can see that the mark time is growing. That's kind of no surprise as well, because the mark time grows as we actually have more memory which is in use, so it's more stuff that the garbage collector actually has to collect. But I think the key takeaway here is that when the garbage collector has to do the sweep and it has to stop all of the work threads, when I'm dealing with one thread, I'm only stopping one core from doing physics. When I'm dealing with 64, I'm now stopping 64 cores from doing physics. So I'm paying an incredibly high penalty. And then this is compounded by the fact that the work the garbage collector has to do is now 64 times worse, because I have 64 times as much memory in flight because I'm running on so many threads. So it's really about the excessive use and allocations that we have inside the package. So how are we going to fix this? So we thought, okay, we really need to get away from this, about hundreds of kilobytes of memory per event, because after all, each event is only being processed in a few hundred microseconds. So the memory churn is enormous in jet reconstruction. It is quite a fast algorithm. So we understand the root cause is we have too much memory which is sloshing about inside of the system, too much churn. So why don't we design a way that we can hold on to the same amount of memory and reuse that during different reconstruction cycles? So what we have designed, this is definitely a work in progress because we're not sure yet how we're going to express this for the users. We want to keep things as stable as possible for them. But the idea here is in this part to have basically a workspace, and the workspace holds all the memory which is going to be needed by the reconstruction algorithm, and then we have a new interface for the reconstruction algorithm where we also pass in the workspace, okay? So now the algorithm doesn't itself need to allocate any memory. It can just use the memory that it's got. We have to do this in a clever way because the amount of memory that you need to do the reconstruction actually varies. So the first thing that the reconstruction algorithm is going to check is, are my buffers big enough to reconstruct this event? If they're not, I'm just going to make them a little bit bigger. But that happens, you know, relatively rarely, and you never shrink again, so you always have, you know, the buffer that's appropriate. I give the example here for also just a very simple version of our chunked scheduler, where each thread is processing an event and then grabbing the next one, processing an event, grabbing the next one, and that helps even out the work queue distribution. So this is what we're trying now. Does it work? Yes. And very well. So the blue line is now Julia and the orange line is FastJet. So in fact what you can see is that not only are we faster again than FastJet at every single thread count, in fact our advantage over FastJet grows slightly with threads because FastJet is actually mallocing and freeing its memory. But of course, because it's C++, it doesn't need to use the garbage collector. It knows exactly when it can do that, so that's why it's scaled a lot better. But what was really dramatic for us, is the fact that we're 92% efficient at 64 threads, which is a pretty good result. And we're also now only using 400 bytes of memory per reconstruction cycle once you've got the workspace. So this has gone down by a lot, about 10 to the 3 actually, about 1,000 times less memory that we're using. But the interface for the users is very much the same. That they get back their cluster sequence object, they do whatever post-processing they want, and then they can just basically give the workspace back to the next iteration. So this is all working very nicely. So this is where we are. What did we learn from this process? Well, we started from a place where our tiled reconstruction implementation was very competitive anyway. The event level parallelism exposed some issues in the scheduler, but it also primarily exposed allocation lifetime costs. We were able to improve a little bit on the Julia default scheduler, but that wasn't really the root cause of the problem. What we found the root cause was memory churn, which was killing us both in terms of allocation time, garbage collection, and having to stop for a very long time when we had many, many work threads in flight. And I guess the key takeaway is that memory allocation patterns, which can work very well on one core, can actually severely inhibit your work when you go to multi-core, because it's only one memory system, man, and it's having to do more and more and more work. So with the new prototype that we have, we can reach 92% efficiency on 64 threads, and we're just thinking about the best way to expose that to the users, and in addition to extend this model of ownership to the other jet reconstruction algorithms which we have. I think Harshit has actually got versions which work for N2 plane and for the E+, E-. So this is all going very well. Now our puzzle is, how do we write the best API for the users so that they can use these improvements effectively? And that's it. That's where we are with parallel jet reconstruction. Thanks.
Thank you, Rin. I'm sure there are some questions. Maybe start with Sam.
Okay, so you implemented your own memory management system. This sounds like the kind of thing that also arena allocators, for example, would be good at.
Sorry, this sounds terrible.
It sounds like the kind of thing that arena allocators would be good at. So, for example, bumper.gl already exists. Did you consider looking at off-the-shelf implementations of non-GC'd things that already exist?
No, that wasn't something that we have investigated. So this is the kind of investigation that we now want to do, is to try and think about the ways in which we can make this as easy as possible for the users, perturbing the API as little as possible. So, we're kind of at the beginning of having proved that this is the problem, and this is how we can solve it. The best implementation of the solution is work in progress.
Okay.
So I think we have time for another short question.
Thanks very much. I mean, I have a quite similar problem, I believe, but I gave up at around your slide 2 in my research. But I was a bit surprised, maybe, because you show a run without GC, and it didn't help that much.
Right.
I would assume it would solve everything. But although even that, when you show that the performance for each thread should be found by other methods, because most of the time was doing sleep.
I was also really surprised by this, for where we got to at the end versus that original garbage collector off run. I thought that garbage collector off would have shown a much bigger improvement given this, but I think we were also paying a huge price in terms of allocation pressure as well. And that's essentially the conclusion we came to, is that having 64 threads which are trying to grab megabytes of memory per second does not scale well either in your memory allocation system. So it's a kind of a twofold problem that did make it a little bit harder to track down. But you can see that as soon as we reduce the allocations, the performance goes right back up. Yeah.
Okay, thank you, Graham. Let's thank Graham again.
Right. Yeah, and at this point, as Uwe is the next speaker, I'm going to take over as the chair. So I will do that, Uwe, who has been your chair up to now, you know very well, and will be telling us about his work at Casus.
If it works out.
Once his HDMI decides to come to life.
Hopefully it will. This looks good. But let's see how I can actually put this thing on. Wait. Do you see that? Awesome. Can you hear me? Also awesome. Hello everyone. Today I want to talk a bit more about how random sampling on GPUs in Julia might work. And I start with a lie, which is also true in some way. Usually when you talk with people about Monte Carlo sampling or any type of Monte Carlo stuff on GPUs, they say, okay, if the different Monte Carlo steps are independent, the thing is embarrassingly parallel, so just throw it on GPU and everything is fine. But the thing is, when you go for a thing called event generation, then some samples will need a different number of trials to actually get produced. Or when you have like a transport code where you go through with the particles through matter and want to simulate that, some particles will fly out of the system like immediately, other particles will scatter thousands of times. So there is like actually a kind of branching just from the randomness and from the random selection you have in these types of processes, which means that the statistical independence of events does not actually imply a uniform execution, which would be mandatory for GPU execution. But let me start with a bit of a motivation why we do these kind of things. And since we're from JuliaHab, we use a Monte Carlo event generation for simulating the data in the very core of the, for instance, LHC experiments in particle physics. So what you see here on the right-hand side is like an event display from the CMS detector, and you see actually one event. And what the event generator actually does is, in the very center where all the lines connect together, they produce these starting events, which then go out to the detector simulation. And just that you see that this is like an important task where a lot of people talking about improving, there are actually 3 papers out there from the HSF discussing how to circumvent challenges we currently have with these types of computations. But also for my very own field, it's laser physics or laser matter interaction, you have similar problems. I mean, what I'm working in is matter under extreme conditions. So you prepare any matter state, which is kind of a plasma, and then you diagnose it with shooting on it with a big-ass X-ray laser. And then the photons actually propagate through the material and then eventually come out of the material you probed and reach a detector. So the whole system is very similar in figuring out how the interactions stochastically work in your system. So it's very similar to the event generation, but here it's more like a particle transport code because the sample we actually diagnose is like a bit extended. And now coming to the method which I want to present here, which is used in event generation everywhere around the world. It's the so-called acceptance rejection method. And here I just show you like a naive implement or a naive description of it. What you need for that in order to draw a sample, call it X, from a distribution, call it f of X. You need a proposal distribution, we call it G of X, which is should be similar to the target distribution, but it should be easy to draw samples from it. And then you need the maximum weight of this quotient there. Say we have that, we have other methods to get it. And then you perform a thing called the acceptance rejection loop, where you produce a trial sample from the proposal, then you draw a random number, kind of a random probability, if you will, and then you check if the probability you have drawn, this U, is actually smaller than the normalized probability given by your target distribution divided by the proposal. And if this is so, you accept the event, and if not, you repeat the process. And just to show you a bit how it looks like, it's on the right-hand side, like a schematic version of it. You have your target distribution, you have your proposal, you combine these two, and you only keep the blue events in the middle panel. And sounds easy. It's kind of trivial. It's a very robust method. It always produces samples which are distributed like F, which is kind of nice. But the problem comes when we go to the actual architecture. Because when the GPU enters the chat, then things might become easier. Usually it becomes more complicated. And what you see here is like a very, very simplified version of this schematic architecture of CPUs and GPUs. On the left-hand side, the CPU, you have different cores, and each core has an L1 cache and a control unit and all these kinds of things, very separated from each other. Then you have the L2 caches, which are shared between different cores, and then you have the L3 cache shared between all cores. And then you have, finally, the DRAM, so the RAM slots you have in your computer. And the thing here is, it is built for doing generic things, doing a lot of things at the same time. They're not specified on very, very specialized tasks, but doing almost everything. And then you have the GPU on the right-hand side, where you have a lot of little cores sitting side by side, which share a little bit of cache and a control unit. And you have an L2 cache for all of them, and then you have the DRAM directly on the device. And the key difference here is that the GPUs actually run massively in parallel all the time. And just to summarize what the key difference is when it comes to event generation is that the GPU is actually great at doing many similar operations at the same time. And then, but the problem is the stochastic algorithms, like the Monte Carlo event generation, they create divergence in the execution because some threads take longer to actually accept an event. Or if you go back to the transport, some particles in your transport code will take longer to go out of the system than others. And this you could in a funny way summarize as that the computer says, it's completely fine, I will improvise if something goes wrong. But the GPU actually says, could everyone please follow the choreography? And to identify what is the first villain in our business here is the synchronization between host and device. So jumping back and forth from CPU to GPU is not a good idea. And here's just a schematic version of how this could look like in a very, very dumb algorithm. So please never do it like this. So you start on the top left side. You have a proposal generator. You generate a proposal. You get a proposal events directly on a device. You apply a target kernel which evaluates the target. You get the weighted events. You want to check if they are accepted. But then you need to memcopy it to the host to do this branching because of the check. Then you have the weighted events on the host memory. You do the rejection filter. It's like the loop for the it's like the checking for the rejection. Then you collect all your accepted events. You check, do I have enough accepted events? If no, I start the whole loop again. If yes, I terminate my thing. I mean, this will actually produce things. And it produces also the correct things. But it's very, very dumb to do this. And the reason is you launch a lot of kernels, which kernel ramp-up time takes a bit, and so on. You have these host device round trips, which especially the memcopy is a very, very bad thing. And then you have this, conceptually, the synchronization between these two, the device and the host. You have it in the main loop, which is also not good. Which means, and finally, or ultimately, that the coordination between host and device is actually taken over all the time, and not the actual computation itself. And here, a joke again, just to shake things a bit up. It's a bit like you buy a race car, but you stop every 10 meters asking if the car's still moving. And the lesson learned here is avoid host-device synchronization in these kind of stochastic loops. It's really important. The second villain is divergence. What means divergence? What you see here is like a schematic picture of the threads on a GPU. So every strip from left to right is actually a thread on a GPU, and every green box is actually one computation which runs on this thread. And as you see, some threads take longer, some are closer if you put the full rejection loop onto the GPU. And this causes gaps. And these gaps are actually unused. So all the threads wait till the one thread which takes the longest finishes. Then you have a synchronization, and then you do all the thing again. And this is actually very bad, because it underutilizes any type of wavefront in your GPU. And it means that even if the loop, the rejection loop, stays on a GPU, threads, the workload actually differs between the threads. And this means that you underutilize your GPU and eventually end up with a worse solution than just running in serial in CPU. And this, a funny joke again, divergence happens if your threads discover free will. So if they start doing things completely in different ways, things got tremendously wrong when it comes to performance. And the lesson learned here is the divergence can usually not be like eliminated. This is not possible because of the random nature of our processes. But you can like squeeze the algorithm around it to minimize the amount of divergence you have. And so now I come to the actual event generator. So I talked a bit about GPUs and what kind of things we need to take care of. And now I show us our type of solution. I need to say, I think it's not the best solution, but it is a solution which works quite well. And for this, I start with the anatomy of an event generator itself. On the right-hand side, you have the input. Input in the sense of what I need to write down in a computer program to start the event generation. And for our case, it's a target distribution. It is a proposal generator, which generates the proposals. And it's a random number generator, which then feeds the proposal generator as well as generates the random probabilities which are needed. And then in the processing step, you do the similar things like I showed you in the naive algorithm. You produce the proposals, you evaluate your target distribution, producing the weights, you produce the random probabilities, and eventually coming to the final step in the processing, and this is the rejection filter. And this is actually the point where the branching actually happens. So all the other things which I explained before are actually massively parallel. So they are completely independent. There is no race condition, no actual randomness in the length of the workload or of the time a thread needs to take to get to a final point. But the rejection filter is, and I will go into detail with this in a moment. And then if you have your rejection filter, you actually only want to dump out of the whole calculation the accepted events. We are currently not interested in the rejected events. And let's come to the actual filter scan kernel. It's like the kernel which does all the rejection things. So imagine you produced your events, you evaluated your targets, and you plunged them together. In particle physics, these are usually phase-space points, which are kind of a group of tuples, and they attach a weight to it. The weight is actually the number I showed you with the F over G evaluated. And then you have your probabilities, and then you have this condition if the weight is actually bigger than the probability. And this flags some of the events green, because they got accepted, and some of them are actually red, so they get rejected. And now the question is, how could I ensure that I write out only the accepted events and in best case in parallel? And for this, every thread which has an accepted event needs to get a kind of an index where it can write into an output buffer. The output buffer could also live on or should live on a GPU, but it needs to know where in memory it can write. And for this, we use a very, very simple technique called the atomic index increment. This is where I think it's not the best way to do it. And what you actually do is you have a kind of pointer to the first element in your output buffer, and every time an accepted event arrives, it does an atomic increment of this index shown there and gives back the last index. So it starts at 1, it increments it to 2, but sends back the 1. And then the same for every other accepted event, which means that every event gets back the last position which was free, and so you can assign it to the actual accepted event, and then you go in parallel writing it out. This actually causes some divergence, but we need to live with that because of the atomics. The atomic means every other thread needs to wait for this one operation. But usually this is fine because this operation incrementing the index is just a single integer addition. Yes, and just to show you like a little bit of benchmarks, I need to say we need to be very, very careful because we show here an implementation using the CUDA backend, and it does not perform very well. It's actually very bad, and we did not figure out why yet, but we are behind that. Okay, what we did here is all of the things I showed you, we implemented using kernel abstractions, just to have different backends and to explore how different backends work against each other in these types of problems. And then we implemented different versions of this algorithm, the last algorithm I showed you. The first one was like a multi-kernel version where every step I showed you is actually its own kernel and launches its own kernel, which has some benefits in the implementation side, but also some drawbacks because the kernel launch time takes a bit of time. Then we have a single kernel version which uses a batch. So you have a batch of things, you iterate on the batch, and then you write out from the batch to an output array. And this has a bit of advantages when it comes to writing down the algorithm because you don't need to allocate anything on the fly. Because you can just write back and forth with the batch array. And then we have a similar version but without the batch, so we allocate on the fly. And just for comparison, I also implemented the native one, so the first one where the whole rejection loop just stays on the GPU and runs there till it's finished. But let me start with the left-hand side, where we have as our problem the so-called multi-photon Compton scattering. For those of you, it's a scattering process. For those of you who are physicists, it's a scattering process described by this Feynman diagram, and iterate like combinations of the outgoing photon. And this process is just for having a little bit of a bigger compute in there, so it's not physically very relevant. And on the right-hand side, we just used one photon, so standard Compton scattering. And what we did there is we benchmarked different number of accepted events we want to have for a fixed batch size. And we used the multi-kernel version here. And we did this for a CPU, an NVIDIA A100 using CUDA.gl, the backend, and Radeon RX 7900 XTX, and an Apple M1 Pro, actually this computer here. And as you see, the CPU is very bad, but to be fair, the CPU version here is just single core, so this is usually our baseline. Then the worst one of the three GPUs is actually CUDA, which is kind of surprising. And we, as I told you, we did not figure out yet why this is the case. What I can say is that this NVIDIA A30 is rather old, and we also need to use an old version of CUDA.gl to actually make it runnable with our drivers. So maybe this is the cause, but it's currently under investigation. But good thing you can see is Metal is quite good, and AMD is actually very, very good on the left-hand side. Similar things you see on the right-hand side. Comparison is kind of the same, but here the most important part, what I want to show you, is the blue dot, which is way off. I mean, it's a logarithmic scale, so it is like a factor of 200 usually off if you go, no, not 200, a factor of 4 when it comes to this parallel execution. And the main reason for that is divergence. It's the main reason for this bad performance of the naive one. And with this, I come to my conclusion. The first thing is independent samples does not mean uniform work. This is the most important lesson I want to show you. Synchronization is usually a showstopper. So if you need communications between host and device in a hard loop, it's very, very bad. You should, when you write these things down or implement these things, you should expect divergence and design your thing around it. This is really, really important, as I showed you on the last slide. And we have next complications we want to build in, which is usually done like replacing this atomic increment by having stacked pipelines and queues in a more sophisticated way. And here are actually the two QR codes. The qd.gl project is actually doing all the work for the target, say the multi-photon Compton and a lot of these kind of things. And in rejection samplers.gl, we implemented all these kind of things. It's currently in a development branch, so it's not in the main branch yet, but we're working on it, bringing it into the main branch. And with this, I end with a last statement. Usually, Monte Carlo is embarrassingly parallel, but it just needs a little bit of help to make it less embarrassing for a GPU. And with this, the logo slide. Thank you very much.
Great, thanks very much, Uwe. So we have plenty of time for questions, so I will open things up. Yeah, we have a question up here. It also gives me lots of time to run around with this microphone.
Thanks for the nice talk. I was wondering, I mean, when you talk about divergence, like at what level are we talking about divergence? Because I think when it comes to like modern GPUs, you talk about like warp level divergence, right? So you're not really expecting like all, say, 1,000 CUDA cores or whatever to be diverging at the same time, but like I think at the moment it's like a set of 32 that diverge at the same time. So could we, sort of take advantage?
It's really hard to understand you. Could you speak a bit louder, or?
Sorry, so I was trying to say that the divergence that we are talking about is happening not at the level of like all the cores of all CUDA cores happening at the same time, but rather at the warp level and current modern day hardware, right? So it's about like 32 or 64 of these that are sort of diverging, and I was wondering if one could sort of come up with an algorithm that takes advantage of the fact that only part of your cores are diverging. For example, you could take the diverging set and then throw them into cache and then like run a dedicated process that only reruns the failed samples, for example.
Yes, that's completely right. I highly oversimplified it here just to show you something. Absolutely right.
Yes.
I mean, the problem we have this kind of things is usually it's hardware dependent. So having like back-end dependent algorithms is really, really hard to actually maintain and implement. I mean, we experiment with this just to figure out how if it makes any sense. And you're right, it makes sense. So we have like a circle buffer which we usually use to cache warp site executions, and this is actually giving us a good boost, I need to say. But it's not that overwhelming as we figured out, and currently we are not having that much manpower to actually go further in this direction because of we want to actually support all the backends, and this is really, really hardware specific, and figuring out what kind of hardware lives there is also sometimes not that easy.
Definitely, yes. Thank you so much.
Okay, thanks. Other questions?
There's a question.
Oh, other side. Coming.
The more questions you ask, the less coffee it gets.
Yeah.
Oh no, it was here in the front. But
I'm just curious, have you considered hijacking a graphics API for part of this? Because it seems like all of this would be, if you're trying to target independence, there are a couple of abstractions that are able to, they're over mesh shaders, but they're able to do this sort of X spawning Y number of threads behavior that you want, yet the work has already been done to make those cross-platform. Have you considered those?
We have it on our list.
What?
We have it on our list. So it is on the list because the thing was for us, I mean, a student is working quite heavily on this currently. I've started with a student. And we have it on our list exploring these kind of things, especially the shader stuff. Yes.
I was wondering, like, what fraction of time is spent on doing the atomic index update, and if that's very different on the different GPU platforms.
I need to say, in our experience, it highly depends on the hardware. Because this atomics increment is actually, I think in some it's just a driver call. And this means it depends really, really harsh on what hardware you have there. We currently also on the list, we have like a benchmark campaign we want to do to actually figure out exactly these kind of things. Figuring out how, profiling what portion of time the actual increment takes. And we have other ideas to actually don't do these kind of things, because it's usually known that even a single increment of a U in 32 is like kind of costly in an atomic. And that's why we want to figure out a way to circumvent that. But we are currently working on it.
Any other questions? I'll just ask one as well.
Yes, sure.
So, traditionally in high energy physics, we've been, let's say, quite conservative with our use of random number generators.
Yes.
So we have insisted upon random number generators which are very random indeed. Possibly, I would say, overly conservative given what we actually do with the events that we generate afterwards and all the chains that we put them through, but okay, very good. Mm-hmm. Do you have a good sense of whether we have good, high-quality random number generators which are suitable for running on GPUs? Because a lot of the random number generators used in the past carry very heavy state with them as well that might not move so easily to the GPU.
What I can say is that, here I used Philox 32x2. And Philox is known for one of the, it's a counter-based RNG, which means it can be used directly on a GPU and utilizes like the massively parallel thing in a way. And this Philox is actually, or the Philox itself as an algorithm is actually known to pass the small and big crush tests, which is like a very, very high bar in a lot of statistical measures on the quality of the random number generator. For instance, Mercedes Twister does not. So this is actually one of the key things why we also use Philox. It's available, but it's also like a really high quality random number generator when it comes to these statistical measures on randomness.
Very good. Okay, thanks for the clarification. So I think given that we're nicely ahead of the schedule, this means that we can take advantage of the fact that our room is right next to the coffee area and everyone can go and grab a coffee, but don't start long conversations. Make sure that you come back here at 11:30 when we will restart the session promptly. So thank you very much to all the speakers. Yeah? Okay, excellent. All right, everyone. I hope you enjoyed your quick coffee. It's time to get started again. So we're very happy that the next talk in the Mini is from Simon, who's going to talk about Mackie's new ray tracing backends, which it turns out is stunningly useful for high energy physics. So take it away, Simon.
Hey, thank you. Really happy to be here and present the ray tracing backend. The image in the background is already done with the Mackie backend. It's using the really amazing simulation output from breeze.jl, which generates really nice clouds. And then if you actually apply real light to it, it looks like actual clouds. So this is very exciting for me as well, especially since I've been using ray tracing since I'm 17 or so. And I've always been fascinated by it. And it hasn't been possible to get it into Julia for a long time, but now it's here. So to show you a little bit what it can do, you already saw some volumetric renderings with the clouds, but you can also use it for fun stuff like the Stanford Bunny. It uses the industry standard Nano VDB to kind of store these sparse grids for really large volume data. And what's really exciting about a ray tracing backend written in Julia is that you can actually implement materials in Julia with callbacks and everything, and you can then implement light bending inside the actual material. And that way you can render an sort of accurate black hole. I think it's not completely physical, but it's a cool start. And I saw on Slack someone trying to visualize the CMS detector with GeoMarky, and it didn't look that impressive, so I was like, okay, I kind of need to figure out how to do this in the ray tracer, and this came out of it. I think it could even look better now, because this is a relatively old render, and a lot of improvements have been happening since then. But yeah, it really helps to have physically accurate materials. So what's the architecture? Marky actually uses Hickory underneath. I kind of wanted to have it in a different package where it just has all the graphics kernels. So it can be used outside of Marky. And yeah, it's support of the PBRT for version 4 volumetric path tracer, which is a really famous C++ ray tracer implementation. It started as a tutorial kind of, and then it came kind of cinematic and state-of-the-art over lots of years. The cool thing for our Julia version is that it's completely cross-platform. So it runs on Apple, it runs on CUDA, it runs on AMD, etc. Yeah. I've got nerd sniped into writing a completely new backend because it's really hard to get ray tracing acceleration across platform. And the only way to really do it is with Vulkan. Otherwise, you just don't get hardware acceleration, and it gives you like 3x speed up, depending on the scene. So I was like, oh, I really want this. And that was when AI got better, so I put Claude Code on this, and surprisingly, it worked surprisingly well. And now we are having this Lava backend, which compiles Julia to SPIR-V and then to the driver on each platform. And the cool thing about Vulkan is that it's completely cross-platform, although Apple is a bit difficult. But what we can do on Apple is that Metal is actually pretty similar to Vulkan. They kind of started together, and then Apple was like, we do want our own thing, but I think it still has quite a bit of the DNA. So I'm relatively hopeful that we can have a Metal backend for Lava. And then we can write vertex and fragment shaders and ray tracing shaders across platform with very high performance. And that also means you can use one array type across compute, graphics, and ray tracing, which is pretty exciting because this doesn't really exist yet anywhere else in such an easy language. I've used this Water Lily package, which is a really nice package I'm sure you probably have seen. It's a relatively complex fluid simulation, and it was a really nice benchmark to try out lava on it. And in the end, I got everything running at roughly 0.65 CUDA speed. It's a very tough benchmark for lava because it launches a ton of kernels and it allocates a lot of memory. So it really also benchmarks the launch overhead and the allocation overhead, where lava still is a bit behind, but the actual compute kernels are usually on par with CUDA. So this is really cool because now you can do the simulation and then even the visualization in the same framework without ever leaving the GPU. Oh. And the performance is really surprising. When I started writing the Julia ray tracer, I was like, okay, we will never reach state of the art. This will be a long process. And I'm happy if it's like 4 times as slow as the state of the art. But turns out, especially with hardware acceleration, we're pretty close to the optics backend, which is NVIDIA's own hardware-accelerated collection of ray tracing kernels. So they're optimized by the vendor. And we're on eye level on a lot of scenes. The crown scene has been a bit of a problem. It's very complex, as you can see here. It's really cool looking and really stresses the ray tracer, but we are somewhat there with hardware-accelerated ray tracing. I'm pretty sure we can close the gap when putting some more time into it. And what's really cool is the C++ version doesn't actually run on AMD or Apple. So we are on eye level on NVIDIA. And on the other platforms, we still have hardware acceleration and the same performance. So this is pretty unique, I think, in the whole ray tracing community because they usually forget about AMD and Apple. So I think this really closes the gap going forward. I had a lot of problems with lava because Vulkan is incredibly complicated. Like a hello triangle is 1,500 lines of boilerplate. And it's really low level. You need to really precisely schedule everything. You need to use barriers. You need to schedule the launches of the kernels yourself. And there were a lot of bugs and segfaults doing that. So I was like, okay, we need a better framework that actually does a little bit of this more high level and automatic, which is Mantle. And it's actually closer to the Metal API than to the Vulkan API because Metal wanted to have their GPU platform a bit more high level. So that also buys us that the Metal backend becomes a bit easier to implement. Kernels are still plain Julia. Obviously, you're just having a bit easier time to create complex programs with them without getting segfaults and weird behavior or lots of allocations. I kind of do plan to also have a CUDA and AMD GPU backend for Mantle, just because it will be very easy, because everything is just a Julia function. It doesn't really matter who compiles it. And then in the Mantle graph, we could kind of figure out when to convert from CUDA, for example, to Vulkan. That means if there's a library in CUDA that you want to use with Vulkan together, kind of, I think this is going to work with Mantle as well. It's not a priority, but I think it will be very cheap and easy to integrate. I've started a little video editor project. So as a stress test, I wanted to run a relatively complex machine learning model on it with Lava. And this is really amazing. We got really close to CUDA on PyTorch, which is the state of the art. And the kernels are super complex. Like, I don't know, like Claude Code ported like 200 kernels or so to get close to this. And that means now like Matmul and stuff like that is implemented in Lava in Julia natively. And it's really close to CUDA speeds on a lot of in a lot of areas. I've also ported some other voice models, which are a bit more complicated because they need Fourier transformation and stuff like that. That is still a bit slower, but I didn't put any time on it, and I'm pretty sure if we port a few more kernels, we can get pretty close there as well. And that's kind of my dream. I've been wanting to have a GPU platform for 12 years or something, where you can do graphics, compute, simulations, HPC, machine learning, and stuff like that together. And the cool thing with Mantle will be that you can kind of optimize across different areas. What's usually a problem is if you have 20 gigabytes of VRAM and your visualization takes 10 gigabytes, your DNN takes 5 gigabytes, and then you maybe have a large point cloud or something which takes another 5 gigabytes, you're very quickly out of VRAM. And if they are all running in different processes and not talking to each other, it's really hard to actually use your VRAM efficiently and maybe deallocate stuff when it's not used and stuff like that. So I'm really looking forward to this as a new way to schedule this. Yeah, what's next? A Marquee backend written in Mantle, basically. That's a Vulkan backend first. And actually publishing all of this, because I've been working a lot on different areas, but nothing is yet registered, but stay tuned for the next month.
Fantastic, thanks. Okay, that's so much cool stuff. I'm sure that there must be questions. And in the meantime, Ilya, maybe you come up and set up your laptop to amortize the laptop swap cost.
So what are you doing in terms of like color management? Is this spectral rendering, or is it RGB, or?
It's spectral, yeah. Yeah, it's quite physically accurate.
Questions over here.
So I was wondering, when you're developing the, I guess, shaders or kernels, do you have a way to like hot swap them as you're editing them without waiting for Mackie to recompile everything?
Yeah, you mean like if you're developing on Mackie and want to have a new shader in there? Yeah, that should work. That should just work like the rest of Julia, I think.
So it works with like revise, like regular Julia functions?
So the caching and stuff like that is kind of inheriting from the GPU compiler stack. And I think Tim does a lot of work on this right now, so we will also benefit from that. And I have a pretty big focus on compile time latency for this, because if it will be the new cool backend for Marquee, I don't want people to wait an hour for all kernels to compile, so yeah.
So thank you for the talk. You had a bunch of comparisons with CUDA, so I wanted to ask you, how do you see this fitting in with the existing Julia GPU ecosystem? I mean, since you also use this for machine learning, for example.
So I think the cool thing we can do in the Julia ecosystem is that we can have normal Julia function run on the GPU. And this is a new way of doing that, and it's not gonna replace CUDA.jl or anything. I think it will live alongside, but yeah, it will definitely open up new use cases which work much better there. But it should be really easy to switch if everything is just Julia functions.
Okay, I'm sorry, but I think we have to close the questions here, but let's thank Simon again. And next up, we have Ilya, who's going to tell us about data analysis in LHCb. Yeah.
Is it also working?
Yeah, it should start to work now. The AV people activate it. Okay, take it away, Ilya.
Hey, so hello everyone. My name is Ilya and I'm a PhD student at the Uni Bochum. And here in this, not working. Let's try another one. Is it better? No?
Try again, say something else.
Check.
Yeah, I see nods at the back, so go ahead.
Okay, so now it's hopefully working. So my name is Ilya and I'm a PhD student at the Uni Bochum. And there we are using Julia quite heavily for the HAP analysis. And here with this talk I want to present to you an example of a simplistic high energy physics analysis, which is completely done with Julia. Before going into actual analysis, I want to show you one slide about the importance of all the things that I will be talking later. So here you see example of this DEMOS initiative, which is doing really important work in the community now, because in recent times, many experiments in high energy physics, they were using many different tools, many different data formats, and that is very important for the collaboration between the experiments and in the community to have some common tools. And the Julia HAP allows to have these tools for the community for doing something more common across the different experiments. So what is high energy physics analysis? What we are basically doing, what we are studying. Mostly this is collider data, so we collide some particles, and then there are many different particles produced in this collision. And we detect them, we reconstruct their track, some other parameters. At the end, we want to know the properties of some new particles, some new physics. And basically, in the example that I have in this talk, we'll be analyzing some toy data, which is shown on this plot at the bottom, and we will try to find the lifetime of this particle that appears here with this peak in the mass distribution. So what we are going to do for that, we will read the data, we will select our events, then we will classify them, we will fit our data, also assign some weights based on different classification of the data, and then we will come to the publishable results. So before doing analysis, it is very important to set up your project properly. So since it's a Julia project, we will have project.toml and manifest there where all other dependencies will be stored. Then it is nice to have some separate folders for different types of files. You have, for example, for data files, for SRC where all your common functions are stored, then for the scripts, notebooks, for playing around. Also, everything should be covered with the test to avoid some bugs, and finally results should be also stored in some separate folder. Now it is already common to use some agents for helping with developing projects, so it is also nice to have this agents.md file where you can specify the rules for your agents, for example, the plotting styles that you want to use throughout your project. Also that the common functions should be stored at in SRC folder, and some other rules that are up to you to decide which you want to add there. But at the end, you're still responsible for your analysis, so validation and interpretation of the results is still up to you. So you will decide either your result is what you wanted to achieve, or you need to do some modifications before going to publication. So let's start with extracting the data. For that, in Julia, we have, for example, these two tools, Unroot, which is a wrapper of the CERN-developed root framework. With that, you can easily read the root file, extract the tree, which is in this case events, and specify all the branches that you want to read there. Then another tool developed by the root developers is XrootD, and we also have wrapper in Julia for that. So for example, if you don't want to keep all your files locally on your machine, you can store them on EOS, for example, at the CERN LX Plus, or if EOS is mounted somewhere in your own cluster, then you can also easily access the files from there with XrootD and again read them in the same way. So in our example, we'll have a file that has this branches, mass of the particle, transverse momentum, quality of the tracker construction, type of a particle, particle ID, and decay time, which will help us to determine the lifetime of the particle. So once we read all this information from the file, we need to apply some cuts to already suppress some background that we are not interested in. For that, for example, you can use data frames, which is a nice tool to easily apply all the cuts in this nice way. So here, this semicolon name of the parameter is basically fields of them in the data frame, and that's how you can easily apply these cuts. Then after cuts are applied, you can suppress background even more, applying classifier. So in this case, this is a boosting decision tree, which is one type of the machine learning classification. Here you can specify some features that you want to use for training this BDT, and then you train your BDT and basically apply it to arrive to this separation of the signal and background, and this variable shows how good you're separating results. So when it's 1, this is perfect separation. When it's 0.5, it's just random guessing. So in this case, it's doing more or less good. That's also showing how good our signal now. So you see that we suppress some signal, some background, but some background is still there. You can either try to play with your classifier by trying to adjust the threshold of the boosting decision tree to find the better working points. For that, for example, I like to use Pluto notebooks, because there you can use the sliders and play around to understand how you want to do your analysis. Then, other way to suppress background even more is to use S-plot technique. For that, you would need to do mass fit, and this is how you can set up your model for the mass fit using, for example, distributions.gl package. Also, there are some other packages available. For example, this distribution.hep.gl has many models that we are commonly and oftenly using in the community. And that's how you can easily set up everything and define objective function for the fitting. Then for the fitting, you can use these packages. So for example, optim.gl that uses BFGS algorithm, Minuit2, which is a wrapper for the C++ implementation of the Migrat algorithm. The new native Minuit.gl, which is pure Julia implementation. And you see that for these simple tasks, they all do all right. They arrive to the same minimum. Native Minuit, which uses stronger Migrat algorithm and purely in Julia, is the fastest one for this simple example. So that's basically just a comparison between them. Then once fit is done, you can calculate S-weights with this S-plot technique. Basically, this is just generalized background subtraction. So you, based on your fit, you're using yields that you extracted, and with this formula calculate S-weights, and then S-weight is positive when you have a signal, S-weight is negative when you have a background, and when you will sum over all S-weights, you will get basically your signal yield back. This is just example, this is just a fit result of this mass fit that used for the S-weights calculation. And here I want to highlight these two packages that can be used for the plotting, this fhis.gl if you want to use some standard histogramming, and this plots.gl if you want to work with some plotting configurations. So then, after we applied classifier, applied S-weights to our sample, you see that our distribution of the decay time changed quite drastically. So without applying in the toy model, which was 1.55. And that's, again, the fit result. And then at the end, when everything is done, when you have your plots, you can save them, for example, with plots.gl in the different formats that you like. You can also preserve all your models with some tables, all your fits results, S-weights. For that, for example, you can use CSV. That's what I'm usually doing. There are some better ways to do this, for example, with Arrow, and there are many other packages implemented within this Julia data organization. And that's basically goes back to my first slide when I said that preservation and common tools across the experiments is very important. So that's how you would arrive closer to the preservation of your results and making them more accessible for the other people in the community. So with that, I'm coming to my last slide. So what I presented is simple example of analysis in high energy physics, completely in Julia. And if you want to do something similar, you would go to these nice tutorials and examples by people in the community and by our group in Bochum, where we teach data analysis course and statistics block course completely in Julia. So please go there and have fun with Julia making your analysis. Thank you.
Thank you. Thanks, Ilya. Perfectly to time. So we have some time for questions.
Hi, thank you for the nice talk. There's actually a question. Did you, when you use all these different types of libraries, was there a moment where you said, okay, there is a thing missing, a thing which I wish like to have, and a thing which is not available, or not available in the way you want to use it?
Yes, yes. There was such moment when we developed, for example, this as plot.gl, because in Julia there were no such package, and during especially our data analysis block course we thought that would be nice. So we first developed it as a part of high energy tools, which has some other nice tools that can be used with analysis. And then we just extracted it in the separate package, and now it's available. Another thing that I would bring up is this fitting packages. So sometimes it is not clear which one is better to use. So you need to do some tests and understand what is the best for your work. Another thing is that sometimes you want to switch between them, and it would be nice to have a tool that can easily allow you to switch between BFGS, Migrat, and not changing too much, because now how you talk with these fitters is a bit different in every package.
Great, thanks. Time for one quick question from somebody. I'll put the microphone between you, you can fight.
Just since a few days ago, BAT now has a maximum likelihood method, which you can just plug these I mean, native Minuit we have to plug in because it doesn't support the optimizers interface, but the others you can just switch now, just use the name, and you don't have to rewrite anything. So
okay, that's
getting a bit closer.
Okay, that's great. Actually, why don't you just, you can go.
Now, very quickly, I assume you have very big data sets. And did you run any problem when using data frames on them? Because I'm not sure.
Yeah, so actually the problem is not just data sets. So data sets, they are indeed big, but Other problem is basically the amount of branches that you usually have. So in this simple example, I had only a few branches from this root file, so that's fine. But when you have many of them, this loading of the files into the data frame becomes quite a difficult process for Julia. For example, sometimes with my poor laptop, everything breaks, yes. So for that, to fight with that, you usually identify some branches that you're interested in. For example, you can apply cuts before loading them into data frames, and then you use some, for example, some momenta to build for momentum of the particle, and that's usually enough for your analysis.
Great. Thank you again, Ilya. And we'll move on to the last talk of the session. So we change a little bit the signal event rate a bit, going from LHCb to Legend. And I'm really happy that we have Florian here to tell us about the use of Julia inside the Legend experiment, which has been quite leading, actually, I think, in Julia in high energy physics. So.
Does this work?
Yeah,
okay.
Good. Okay,
perfect.
Take it away, Florian.
Okay, I'll put this here. Great. Okay, thanks. Yeah, my name is Florian. I'm from the Max Planck Institute for Nuclear Physics in Heidelberg and the Technical University in Munich. And as Graham said already, I want to switch topic a little bit and tell you a little bit about Legend and the experiment and what we're doing there. And I try to do 3 things in one talk in 25 minutes, so I hope I succeed, which is telling a little bit about what we are doing, because it's not the classical high energy physics topic like LHC physics or so on. I want to tell you about the Julia way we're doing it in there, so the Julia software stack and what it is involves, and then give you some analysis highlights and like, okay, how do we apply our Julia packages and routines to the data, and want to summarize in the end a little bit. Okay, let's get started. Since I don't know who is familiar with it, I want to give a brief physics introduction. So the Legend experiment itself searches for the so-called neutrinoless double beta decay. And this is interesting because it's basically a decay of a nucleus where you have, in the standard way, in the standard model, an allowed process with 2 neutrinos emitted. But if you don't have any neutrinos, you would find beyond standard model physics. And in particular, you could prove with this lepton number violation with 2 units, prove that neutrinos are Majorana particles. And this is very interesting for cosmology because it might be an explanation for matter-antimatter asymmetry. There's a huge study and searches going on. There are a lot of isotopes, roughly 35 candidates where you can do this in. In particular, if you want to look for this, what we're doing there is this classic beta decay search. So we have this double beta decay with 2 neutrinos, which is just a continuous spectrum. And you see already it has a half-life of 10 to the 21 years. So that's the whole challenge for giving an order of magnitude that's 11 orders of magnitudes longer than the age of the universe. And then what you do in the end is you look for a peak at the endpoint, because this is where all the energy is contained in these 2 electrons which you measure. And then you expect the current best limits are in the order of 10 to the 26, and we're now scanning up to the 10 to the 28 years. This is in particular challenging because what you want to do, of course, in the end is you want to suppress this background in this endpoint region as much as you can. That's the whole goal of the analysis and all these experiments which cover basically the topic of neutrinos double beta decay. Okay, how are we doing this in Legend? We're using germanium detectors. This is the main point of the analysis. They are basically semiconductor detectors or volumetric semiconductor detectors which we enrich in this germanium-76 isotopes which can undergo this double beta decay. So we have our source as the detector, but the detector is not really decaying because the half-life is so long that nothing really happens in the end. The rates are really, really low. And then we purify them and then enrich them, as I said, make these crystals, and then can use basically the properties of the germanium detectors itself with the excellent energy resolution and the option to do topological discrimination for the whole analysis. How is this done in Legend? So this is an experiment in 2 phases. The first one is this Legend 200 phase, and then there's an upgrade phase in the beginning of 30s with 1,000 kilograms. But right now I'm mainly focusing on this Legend 200 program, which is in Italy in this Gran Sasso laboratory with 200 kilograms of these germanium detectors, and we're taking physics data since 2023, so it's a rather new experiment. Okay, this is how it looks like. We have 3 systems. You have these germanium detectors, as I said, these semiconductor volume detectors. They are like then put into the string configuration surrounded by wavelength shifting fibers, where we can read out scintillation light from liquid argon, which is surrounded there. So this whole thing is in a liquid argon cryostat. And this whole thing sits in a water tank, which we use as muon V2 in the end to reject cosmic muons and all the event topologies they can produce in our detectors. Okay. Maybe a little bit about what we're doing with this, because it's then important for the analysis and what Julia comes into play into this. So I said we have these 3 systems, and then what we do in the end, we do a lot of background rejection and basically analysis strategy based on the fact that all these double beta decay events are just single energy depositions in these detectors. And then you want to reject basically different background topologies, for example, coincidence signals. So you have to somehow do coincidence tracking. You have coincidence signals also then either between 2 detectors or, for example, for these muons between the argon or this water tank. Then you want to reject events which scatter, for example, in one detector and only deposit in the liquid argon. So you want to read out this light and effectively reconstruct a light signal there to reject these events. And then you do particle discrimination with this pulse-shape discrimination method to reject Compton-scattered events in one detector and alpha and beta decays on the surfaces of them. And on top of that, we have much more scintillating plates and materials in the system, which helps you discriminating and rejecting this. This is how it looks like in the end. This is a picture of the setup. So these are the real detectors. And then, for example, there are these 140 kilograms installed. As I said, we're taking data since 2023. And then just as a visualization, this is like this light output you generate when you put a UV light into the strings. This is how all these scintillating materials look like in the end. Okay. This whole legend mission in the end is running, and we had these 2 phases and so on. There's a first result. However, today I don't want to focus on any of these results because I mainly want to focus on the analysis strategy and, as I said, about Julia and this secondary analysis we have in there, which is called Juliana, the Julia legend analysis. And in legend, the strategy here is basically we go with 2 analysis routines, 2 teams, and like 2 kind of like software stacks. The first one is in Python, it's called PyGamma, and the second analysis is in Julia called Juliana. In particular, we want to like basically have method developments with 2 independent stacks and teams, and also benefit in the end the robustness of this result. Okay. Over the course of the last 3.5 years or so, this was all developed, and the Julia Legend software stack is what came out of this. And in a nutshell, this is basically the slide where I could stop now, because it's it. It's a full software stack for a full experiment, going from tier-like structures, from simulations, up to a final result you can put in a paper. And in the end, this is a big slide, so I want to walk you a little bit through it. In the end, we have basically here 2 sections. The top one is official Julia physics packages. So these are packages in the Julia registry and are under Julia physics, which like are developed by the Legend team, but are really the purpose is not just Legend, it can be applied by any other experiments and are already used by other experiments. For example, for simulations, for signal processing, spectral analysis, or for Bad Deutsche Ale for the statistical analysis in the end. And then what we did in Legend is we have our own registry, and then we developed a set of Legend packages. So they also all start with Legend in our own registry, which then take these more general purpose packages and then implement the routines we actually use for the experiment for the analysis. And this is all encountered by like 4 things you need on top, because you need something for I/O, read-write data, you need metadata handling and parameter handling, you need somehow to connect to HPC centers to do your data flow computing in the end, and you want to plot and have nice plotting packages in the end for style guides and so on. Okay, if you want to check this out, you find all the packages in the top row under Julia Physics, as I said, and the other ones, this is this Legend -X GitHub, so if you want to check out, just go there, select Julia, and you will find all these packages and their code online. Okay, in the third part of the talk, I want to now go ahead and basically tell you a little bit about the analysis highlights and how this whole software now is applied to the data of Legend, and then what this looks like. And what I try to do there is like to go with the same highlighting as before, to go from raw data or simulated data up until the final result. And now I want to walk you basically through this Legend step by step and give a couple code examples. However, I cannot give as much code as I wanted to, so I want to do a little mix between a little code, a little plots, and a little explanation what's going on, and hope I can walk you a little bit through like how this is whole built up. And just at first, I want to highlight here that this whole chain now is purely in Julia. So now nothing you will see there will have any other code dependencies. This is all really full Julia, going from raw data, which is taken with Pyramid, and then opening it to file up until you do the plot for the paper. It's one Julia code, one pipeline, end to end. Okay, before I start with starting with the raw waveforms, just this all put together, it's actually quite interesting because the first thing you need, as I said, is somehow to later go through this full pipeline and data flow for the HPC computing. And in this context, they have this package called Juliana.jl. And what it does is it's a custom implementation of our pipeline and data flow in there. And this uses a package called parallel processing tools, in particular to be able to dynamically and do interactive scheduling on Slurm-based clusters. So what you can do there is you can just basically open a Julia session, connect to Slurm, and then access of the computing center as many workers as you want, as many nodes as you can get. And then you have a lot of nice things in there. For example, on the right now you see, okay, we have this flex worker pool. I allocated, so far I have only one worker, which is my main, and then if I execute a script, for example, I can allocate here millions of workers and can really do this interactive in a Julia REPL shell. That's quite nice because with this method you do some kind of interactive HPC computing. That's the best term I found so far for it. And then in this package we build out the nice things in there. For example, we have timeout mechanism, atomic file creation. In Legend we use HDF5 files, so we have quite nice performance here in terms of read-write. We scaled this up and run onto this Max Planck supercomputer facility with up to 4,000 parallel multi-workers. And then we have, of course, also a lot of things under development. For example, an improved progress monitoring and general performance monitoring is a bit lacking. Better reporting, better logging, and also a better kind of compute graph capabilities in this whole data flow that you'll be able to also maybe use this a little bit outside of Legend, that it becomes more like a standard tool for simpler workflows and so on. We tried Dagger for a while. I want to mention this, but it was not really useful for our case and missed a couple things. So this one is, I think, a simpler version of Dagger because the graph computing parts is only for simpler problems, but I think it's much nicer to use and much easier for these middle scale experiments for example, Legend. Okay, then the way we use this, it looks then like this. So there's all built in this Juliana frame, so you just execute, you set basically one variable where you point to the data on whatever machine you are. This works on a laptop, but also on an HPC center. Then you execute this data flow, and this whole thing opens. And then since it's interactive, you always have a menu with a lot of options where you can say what you want to do. You can execute one tier. You can say, I want to only do the signal processing, only do calibration threads, only do the high-level analysis. I can select the periods, the runs, whatever I want, all very interactively in one little shell, which is also quite nice for new students because everyone is used to REPL, but maybe these super complicated tools like SnakeMake or so on might be a little overkill if you're just a beginner and you want to see how this works. Okay, this was my start for the HPC part. Now let's dig into some analysis. As I said, first part is usually the raw data. In the raw data in Legend, we are using the full digitized waveforms as our input data, so everything is stored for offline processing, order roughly 100 channels and 50 SIPM channels. We have metadata in JSON or YAML, and then on top of that, we have everything else in HDF5 with some custom compression. You can see here, this is how the raw signal looks like, and typically a Legend week consists of a calibration run with a source, and then you take physics data where you then later measure this double beta decay. And then to open this here, you can use this data management tools and HDF5 toolings and then select, for example, a period and a channel or so on, and then you just plot some waveforms. This is an easy way how to access this. And everything also here usually has this data opening, and then we have these tables coming out, type tables. And then if you want to plot something, there are a lot of plot recipes, for example, this waveform plot in Maki defined to get these nicely plots out of there with Juliana decide tags and so on. Okay, but apart from the raw data, also what you can do is you can simulate data, and there we have a package for detector simulation called solid-state detectors, and this implements the whole solid-state physics of germanium detectors. You start there with giving it basically a bias voltage, impurity density, and a detector geometry, because this is somehow the crystal you want to simulate, so you need this as an input. And then you just say using solid-state detectors and give it a YAML file where you put all this inside. And then what you can do is you calculate your electric potential with a function called calculate electric potential, and you get this nice plot out there. The next step you want to do is calculate your electric field inside this detector. You can see that typically these detectors have here a P-type contact. Inside it's a P bulk and then an N layer at the outside where you apply a reverse bias voltage on that. That's why all these field lines moving to this point-like contact there. After you have your electric fields, you can apply a charge drift models and then actually start drifting the charges. So for example, for an interaction point here, you create electrons and holes and then they drift to this contact. And this you can actually then do to then define this weighting potential, so which tells you later like, okay, how much when I drifted towards the contacts in the end by like doing this for the two kind of like contacts, which is this N contact and this P contact. And after you have the weighting potential, you can then actually calculate the raw pulses in the drift path. So on the right here, you see a simulated raw pulse by basically going through this whole chain, applying these like, I don't know, 10 lines of code, and then in the end, you end up with a raw simulated pulse. And then if you want to do this in a little nicer way, you can also then, for example, define the energy position at the Cartesian point, deploy one NeV in there, and then simulate, also do a many-body simulation where you see here the holes and the electrons, how they drift, and where actually there's self-repulsion and diffusion applied on the fly, and then you get a nice Julia Giffey out of this. All of this, you find the solid-state detectors. Here's just a screenshot of the very nice documentation online if someone wants to check this out. But now a little bit farther, because actually new and in my opinion very cool, because on top of that you can also now do Geon simulations, because if you just load using Geon 4, we build a very nice extension to this, so you place a monoenergetic source, for example a gamma source with 2.6 MeV at the side here, and you say, okay, I want to build a Geon 4 application out of the simulation and my source, and then simulate 10,000 events, and there you go, you have a Geon 4 simulation, including all detector physics in one go in a Julia session in, I don't know, 8 lines of code, something like that. Okay, and then of course, after you've done your simulation, you can also simulate your waveforms and then, for example, apply electronic models, noise and so on top and really feed this into your signal processing. So I think this is quite nice. Okay, after you have data, you then want to do something with the data. Typically with real data, you need to remove some like non-physical events and like really get rid of some garbage, as we do with some machine learning technology in this LegendML package, where we basically classify all our signals into these 14 categories using support vector machines and some other technologies, and then do some relabeling with Bluetooth notebooks by hand during the shifts. This allows us to select basically some, I don't know, weird events you usually trigger on and you want to get rid of before you do anything. So you want to basically use this as a data quality assessment stage using some machine learning approach. After you've done this, you need, since we have raw signals in Legend, to do signal processing. So you want to apply filters to actually extract parameters like energy and so on from your raw signals. Okay, the way you do this is with a package called Radiation Detector DSP, which is in Julia Physics and our Legend routines in Legend DSP. And this is an implementation of just generic filter routines which you can apply to your signals. For example, here you see a trapezoidal filter. You can do pole zero cancellation. You have timing filters, trigger filters, integration filters, derivative filters, all basically to get access to whatever you want. For example, the signal height contains the energy information. All of these filters, they have like GPU accelerated DSP routines, so actually you can run this on a GPU if you want to. This is not yet fully done, but most of it already works, and this is something we're now really targeting to really scale this also up the full GPU processing for the full pipeline. And here, just as an example, how this looks like if you do this in Legend, so you load this Legend DSP package, just say DSP ICPC, which is the one DSP for this one geometry, and there you go, you enter a table, a config, and everything is there. Okay, next step is energy calibration, because now you have raw triggers in the end, so you have some information about the energy, but in the ADC scale, so we need to convert this to a physical unit scale. This you do with a calibration spectrum. You can see one here on the right. In Legend, we use a Fourier source to calibrate every week. This is like the spectrum, how it looks like, with a very prominent peak at 2.6 MeV. This is the decay scheme, and how you do this in Julia is basically load this Legend specfits and always Legend Maki, which are our recipes. And you can just say, for example, a simple calibration by give it the uncalibrated energy and known gamma lines you input there. It does everything for itself, exports like the right scheme, and then you get a report tuple back, which you can just plot. So for the user, it's quite nice because the first thing always contains a result with just the information what it did, and the second object is plottable by saying lplot, legend plot, give it this thing, and then this pops out in the end. Okay. After you've done basically some, or got some assessment of the energy scale, you still want to do a little bit more of the energy. In particular, you want to fit all these peaks. And this you can also use Legend spec fits for, because this peak model we are fitting for this gamma peaks typically consists of 4 components: Gaussian signal, a tail component for lower energies, a background term, and sometimes a high energy tailing components for some special type of peaks. This now sounds horribly complicated, and Juliana, it's not, because you just say fit peaks, give it some histograms, some pre-starts, you calculated some namings, and you say L plot, and all these peaks basically pop out. This is based on BUT and this Bayesian guided MLE fits in the end, and works quite nicely. What we've done so far is like, yeah, for each spectrum, usually fit 8 peaks or so on, and then you do this across 100 detectors, across 50 runs, so it's quite stable, gives you access to the uncertainties, residuals, and so on, and this works really well for our case. And then you do 2 more things, which is quite simple. You do energy calibration, so you calibrate the ADC versus the KV scale. Don't think I have to go into more details here. And then also you want to access the resolution, because it's very important for the search in the end, where you just fit basically square root of a first order polynomial to this, to the end, do a full with half max fit of like all the values you extracted so far from your peaks, and then get access to basically your resolution at this Q value where I want to do the search for legend. Okay, this is how this looks like in total. As I said, we have roughly 25,000 spectra, and we can just deploy this on the go, and this works really well and nicely for legend. So I think it's quite impressive result that we managed to deploy the software stack, and now you can calibrate anything, and you never get any errors or fails, and you are really debugged a lot there and can do this for any type of combination of spectral analysis you want to do. Okay. Last but not least, one thing we're missing in analysis in germanium detectors is this pulse shape analysis, which I now want to mention a little bit. In particular, this is a topological discrimination to discriminate the signal events which are here on the right. So basically a single energy deposition versus alpha betas at the surfaces and Compton scattered events inside. And the way we do this is you see in this dark blue always this waveform signal you saw from before, and if you take the derivative, you end up with this light blue, and you can see already that you have an acceptance region here with this light blue where these single side events fall in, and all the other topologies have other classifiers in the end. If I plot this in 2D for one of these calibration spectra, you see this calibration spectrum here again on top, and then you see as a 2D histogram this classifier versus the energy. And then you see in here that there are like different regions, particularly here's this acceptance band, and these gamma peaks, which typically are like Compton scattered inside the detectors, have a certain lower value features for this classifier in the end. So we can use this by basically using one peak, this double SK peak, where we know we have a single energy deposition inside the detector, as a proxy, tune this cut onto this, and then reject basically background events based on, okay, they don't lie in this region because they don't fulfill this. The way we are doing this, we're using this proxy peak, as I said, and then you just can tune a cut so that you in the end up with 90% survival fraction in this peak, and what you see here is basically the survived peak and the cutted peak, which are simultaneous fit with a fit routine, and then you do a cut search by like scanning for lower cut values and going up and up and up until basically the ratio between the two of them is like 90% is in the survived peak and 10% in the cut peak. And this is all very nice, like hidden in this very cool routine function in there to do the full bullshit analysis on the go. And then in the end, you also set a high cut just at 3 sigma, so in the end you end up with a little lower section, because then you can also reject these type of events on top of that. Okay. And then just as how this looks like in numbers is if you apply this for a peak where you know you have, for example, 2 energy depositions in the detector, so this is somehow multi-site, then you end up with 5% in the end of like, well, roughly between 5 and 6% of like survival fraction. So you suppress the background, the Compton background by 95%, and this you can all get access to also with these peak survival fractions, which always what they're doing is they're doing a simultaneous peak fit of this peak ship models of the survived and the cut peak in one go. And as a visualization, this is how it looks like on the spectrum. So you see, for example, in the zoom region here, this one peak, which is single side survives, and the other one basically goes. And this spectrum is quite nice because it's like an overlay of like all 50 calibration spectra, so super high statistics of all legend data which was ever taken. Okay, and with this, you're at the end, because what you can do then is event building. And event building just means taking all what you had before, throw it into one pot, and then build or reconstruct your events to end up with a spectrum. And as you've seen here, this event building happens in this legend event analysis. This basically does the software triggering, as we call it, and the reconstruction of the events by combining this free subsystem and all the information and data you extracted so far in the pipeline, and then building basically these coincidence flags for the germanium detectors, this liquid argon veto system and the muon veto, and these event level pulse shape flags extracted like I showed just before. And then what you see here before all cuts, you see the raw spectrum here in gray, and then this hypothetical 2-node, 3-node double beta decay line there. So this is like what you measure after the event building. If you don't do anything, you just have all the flags behind here. I just plotted now, of course, always the one observability energy. Everything else is somehow hidden still in the data. And then on top of that, yeah, you can calculate some efficiencies. Okay, how well does this work? Because of course not all cuts are 100% efficient. But then on top of that, what I can do, I can apply more cuts. For example, now you go from this gray to this green with this pulse-shaped cut. In particular, you see now that you suppress the gamma lines and all the alpha continuum is gone. And then in the next step, you apply then also with this event builder, this liquid argon V2 cut, and then you end up with this red spectrum, which follows quite nicely this 2-node, 3-node line. So, okay, so we did something correct here, and then you end up here with basically the signal region, because here you would expect, hypothetically, this peak if you would find this double beta decay, and then you're done with that. Okay, and then, since I'm running out of time, we are skipping one slide, because in the end, we want to like do the final double beta decay analysis and get our half-life and background index. And for this, you can use the SPUT tool, but since I don't have really time for that, I will skip this, but maybe we can ask questions about this or talk a little bit about it later for the statistical analysis part, because in the end, with all of this, we have now very recent in May done an unblinding to really have a proof of concept for the full pipeline, and this unblinding result is basically the last slide, which I wanted to show here, which basically meant this is a result which is full Julia from the beginning to the end, inclusive, also taking into account all the statistic analysis, and you see here the final energy region. We didn't find anything, so there's no neutrinos double beta decay yet. However, we have the first half-life limit and background index with full end-to-end Julia pipeline, including like all the analysis I showed so far, and there will be soonish a new paper coming out which will summarize all our efforts in there. This brings me to my summary and conclusion, and I just want to leave the slide open and thank you all, and would be happy to take some questions.
Thanks so much, Florian. Yeah, indeed, we're open for questions. So, Uwe first.
Yeah, thank you very much. Really, really nice work has been done there in Juliana. The question is, I mean, I think the question was there in another talk as well, but you have a lot of packages depending on each other. How do you make sure that they actually work together if you change something in some package?
I think our dependencies are not that big as it looks like. Maybe I can go back to the slide with the software. Because in the end, the dependencies only go down, so vertical and not really horizontal. So actually, it's quite nice because these ones here, we make sure that we always upstream to Julia Physics and have the really generic routines, and these are never touched, or there's not that much which can you break. And then if you go down, here's really the legend-specific code where you change much more. So I would say the development rate here is much, much lower than here, and typically there's not that much which breaks. And what we try to do actually to avoid this is we try to implement and do feature development in this lower area here in the legend side. And then as soon as we are happy, for example, then we go up and write a nice API and then put this up here into the Julia Physics to make it more community-wide. And I think with this approach so far, we managed to not really break a lot of things, and the dependencies are not that great. Because then also we have we use a lot of extensions and so on, so it's not really that big of a deal, I would say, in our case, yeah.
Thanks, Florian. So more questions? It's all too good. I mean, maybe one which I have is that you make things very easy for new students, which is great. How do you guide people towards actually learning stuff versus just running a recipe? Because if we have like one big red button and it says, "Give me results," student learns how to press big red button, fantastic, but they don't really learn anything. So what is the kind of the process by which people say, okay, now I've got different analysis, I need to do something different, which package do I touch, how do I do something new?
Yes,
here?
I think it depends on what the student is working on. I'll make an example. If you want to work on this, let's say, energy calibration, you typically only work with these legend spec fits package because there's where the fitting is inside. So this package they touch heavily and do revise and so on. But what wanted we to take off the boilerplate in the end, this code you don't want to touch is like, okay, now I want to apply this to all 100 detectors, span it on a huge HPC cluster, so there's no need for them to write now Slurm configurations, because this they just run and do black box and press a button, and they only touch the part they actually want to use, because this scaling is not really necessary that everyone becomes a Slurm or HPC expert. What they should be expert in is like the physics parts. Okay, now what can I tune in my specific case for my fitting or whatever I want to change or work on in the end as a student. This is the approach we're taking.
Thanks. Oliver, a comment on this, maybe?
Yes, my one addition, we also got into the habit lately of having an extra day before each collaboration meeting with an in-person tutorial workshop day, both on our Julia and Python stack, and show some different things every time, so both for new people in the collaboration, but also to remind people, oh, actually, if you want to look a bit deeper, that's in this package, that package. And I think that has been very profitable.
And maybe to add to this, what could happen in the future is that we managed with some of the packages now that is used across collaborations. So there are other teams already who are using these Julia Physics packages quite heavily, and maybe this actually will become more and more the case, so that it might make sense to then maybe go beyond one experiment and get together and do a workshop or something like this for radiation spectral work, I would call it in the end. Yeah.
Great. Okay. Unless there's another urgent question, then I think we can move to the last session of the agenda, where I think we say goodbye to our YouTube audience and we have more of a roundtable discussion, which is a bit easier to do in person. So I hand the microphone back to Uwe to introduce this.
Let's thank all of the speakers in this session.
Yes, thank all the speakers again. Thank you very much. Yes, let me set it up a bit. So, I use the time it takes to actually set the thing up.
also a member of Julia Hub. All right, so today we'll present a bit about a package we've been working on about electrodynamics. So we'll begin with the introduction. I believe the best introduction is in this video. So as you can see, the field that's coming from the left side is an external driving field. We describe analytically, you might know Laguerre-Gauss beam. It has a characteristic screw-like shape, which interacts with an array of electrons. And then, because these electrons move, naturally they will produce radiation, okay? And then what we are interested in doing is finding a way how to compute the coherent radiation emitted from these electrons on a screen placed a certain distance away. All right, so in a nutshell, as I said, we have an analytic expression for a driving field. We can like solve the three Maxwell equations, and we get an expression for a laser, or maybe a different kind of beam, and then we use this expression to drive the electron dynamics. We'll consider the electrons relativistic, but not quantum. And finally, because we can find the trajectory, then we can calculate the radiation that's emitted at a certain point in space from this point on, okay? So theory-wise, basically when you have relativistic electrons, their motion is described by, there are multiple, not just one formalism, but in short, we've chosen the manifest covariant formalism because we found it's most performant. In this case, each electron is characterized by 4 coordinates, right? And the integration is done relative to a proper time. So like if you know the twin paradox from special relativity, the integration, the motion is done from the point of view of the internal clock. So what you have on the top line is the set of 2 equations, 4 plus 4. All right, so then we have a known shape for the field. This is the Laguerre-Gauss beam. As I said, this is a corkscrew. So there's like a very long formula here. It doesn't matter really. What matters is that it's got an interesting topological charge. That corkscrew action is given by the whole number in the azimuthal dependency. And we also have a plane wave-like characteristic to our field. So basically what happens is that the electrons are accelerated and then decelerated and then accelerated again. And that makes numerical integration very difficult, right? So because we need to somehow constrain the motion to be finite, we also use an adiabatic envelope to introduce the field gradually and then extract it at the end. This is like prototypical Gaussian, but we can also have Gaussian wings, etc. Right, so what happens is that you have this corkscrew-like structure, as I mentioned, and we hit our electrons with it. Then, once we have calculated the trajectory of our electrons, we can use the analytic formula. And then we are interested because in Romania and in many other places, you can modulate these kinds of fields and you can actually hit electrons. We are interested in finding the radiation. And usually it's good to somehow filter. So by doing a Fourier transform over the field we compute, we can maybe produce something that experimentalists can see. Okay. So why are we doing this? Because during my PhD studies, I've found that there's a way to analytically approximate the field you obtain when you compute this interaction. And if we can, with a cascade of approximation, then probably there's a numerical method to do it exactly without any sacrifices. So to do it completely. Okay, so there's 2 main challenges here. First, you have to integrate a set of 4 plus 4 ODEs. And the solution is very simple here. This is part of a paper I did before. Basically, if you use differential equations with Ver9, the problem is basically solved, and you have parallelization for free because our electrons, we consider them screening each other so they don't interact. So basically, we have a free parallelism. Okay. And the second more difficult part is that in theory, when you compute this theoretically, when you do the cascade of approximations, you tend to sweep up the problem of synchronizing the radiation because this is what makes coherent problems, right? So what happens is that in special relativity, because we basically coordinate everything relative to the internal clock of the particles, if 2 electrons are very far apart but they are moved by the same wave, so like this, then this electron will only see the information coming from the other side much later, right? So the issue is that when we go over the screen for each pixel, we must synchronize the radiation incoming from every electrons in our distribution. Okay, so as I said, basically there exists a known analytical formula. If you put an electron in a plane wave, you get a periodic motion. This is known for a long time. So basically you have this f of x and z, which are two of the coordinates of the electrons, and it's parametric. So basically if the trajectory is correct, then you should get 0 from this equation. So basically what happens is that depending on the solver you use, you can get a closed loop or not. And this is like very representative for our case because we do not assume periodicity because we have a lot of oscillations, but they are not symmetric, right? So yeah, I ran a battery of tests. Basically, I've run more or less every single solver you can find in differential equations, and I found that Venn9 is by far the best and the fastest, and also memory efficient.
Okay, I'm Sebastian, and I'm going to continue the talk here with the actual implementation in the package that we have describing the radiation now from the numerical point of view. So far we've seen that we have some analytical approximations for how the radiation of the electron behaves, and now we want to go further with a numerical method that can describe this. And in order to describe this problem, I chose to use modeling toolkit, and I'm going to demonstrate also why this is an efficient choice in this case. So we want to separate the description of the physics from the actual performance optimizations that we might want to do so that it's much easier to read off and verify the physics part of your code and not just stare at very hard to understand code. So here we have a description of the ingredients that we need. We have an external laser field here. It's a Laguerre-Gauss laser. And we have a description for the electron dynamics. And then we assemble these systems. And with MTK, we arrive at a system of ordinary differential equations that would be almost what we would do if we were to write it by hand, but with a lot of compiler optimizations that MTK does. And here, essentially, with the approach in modeling toolkit, we want to describe what do we know that is true about the system. So what are the equations from the physics point of view? And we don't particularly describe how do we actually numerically solve this. This job is for the modeling toolkit compiler to do. And when we do this MTK compile step, we get to the actual set of minimal systems of equations that we want to actually solve. Now, why would we want to do this, and why is this an interesting approach? Is, for example, when we want to make our model take into account more accurate physics. So what we've said so far is that we have electrons that are accelerated and they emit radiation. But when the electron emits radiation, essentially we don't encode any effect of the radiation emission to the electron. So in order to take this into account, there are several approximations that one can do in classical electrodynamics, and one of the best ones is the Landau-Lifshitz equation. And essentially what I wanted to say is that with modeling toolkit, we can symbolically take the derivatives, and we don't need to do this for every type of external field. So this can get very complicated, and now it's just one line. And then the radiation is computed on the GPU, and we have the results, and they match the analytical solutions in the limit of small laser field intensities. And thank you for your attention. And if you have any questions, let us know. Yes?
So yeah, this is the benchmark I ran was to put the electron in an external field, as I said, the plane wave with specific initial conditions, and run with pretty much I scraped the ordinary differential equations for all the solvers I could find and make work, and I put them in a benchmark test. Any other questions? So really the hard part here is to synchronize the field emitted by every single electron. That's the hard part, and that's where we needed the GPU. After we optimized the Audi solver, the trajectories are non-factor. You can compute them on a CPU, and you will, with very few electrons, get good interference diagrams. Thank you. So go ahead. Go ahead.
You mean in like runtime, how much does it take to run one simulation? Yeah, so for example, on an MI300X, these simulations take about an hour, and they take around, depending on the screen size, so as I'm showing here, that we are parallelizing on the screen size. If you want a decent resolution, you would need around like 100 and something or 90 gigs of RAM to like 170 gigs of RAM, depending on what other parts you are interested in on the physics side and frequencies of the radiation and so on. Yes? In this case, we're using double precision. So we need very accurate computations for the retarded time, so that, because the computation of the interference pattern is quite sensitive to precision, so we're going for double precision, which is going to take more time. Thank you.
If I prefer it. Yeah. Okay, next speaker of this session is Jeon-Hoon Lee, and he is telling about Akalim 2.0. Please start. Yeah, great.
Awesome, yeah. So thank you. So yeah, I'm going to be presenting Aquarium 2.0, really on how we're using it on realizing real-world robotic swimming with differentiable fluid structure interaction. So in this age of, so I come from a robotics background, and in this age of humanoids, manipulators, VLAs, people are asking, why should I care about, bio-inspired swimming robots? And this is why I really show them where if we look at nature, you probably notice that fish are really good swimmers, right? They can swim in schools, they can do leaps out of the water. But if we look at, our robots that are out there doing underwater exploration, they're a little bit clunkier, right? Or a lot clunkier. They're slow, they're made for long oceanographic surveys, and they satisfy most of the use cases we want them to, but this still kind of begs the question, right, of if fish really are so much more efficient, maneuverable, just, really better in locomotion every way, why aren't there more robots swimming like these? And that's not to say that we haven't tried. So this has been a very interesting topic, especially in the hydrodynamics community, where really since decades ago, this really got spun up by research from MIT on trying to realize fish-like swimming. And fast forward to 2018, we finally start seeing soft flight fish robots deployed in the real world, but they're still automated by, controlled by human divers. And robots still are coming out, but none of them are really autonomous. And kind of the question is why? Why can't we design good robotics policies for these things like we do with humanoids and manipulators? And one of the reasons that during my PhD that one of the reasons why we thought that was because of the modeling, where it's really difficult to model these systems because you really have to model the multi-physics behind it, specifically the fluid structure interaction. So this field has been very prominently studied by the aerodynamics and hydrodynamics community, specifically for like these engineering analysis applications like aeroelastic flutter. But very recently, we finally started seeing a lot of these kind of multi-purpose robotic simulators come out, like NVIDIA Omniverse, Genesis, where really the emphasis is good visual rendering. So the emphasis here is how do I simulate my physics so I can get good visuals I can then send to train my vision-based policy, VLA, or and whatnot. And so a lot of those tools are very particle-based because I need particles to render. And in this work, we kind of try to see, okay, is there a way to combine these two? Can I get the good accuracy that I need for the swimming case that we have in the CFD community and combine it and still have robotics features that we care about that we see in these more multi-purpose robotics simulators? And when I started my PhD, we figured Julia was a great starting point because there was, at the time, back in 2021, a lot of really nice toolboxes started to spin out. So things like Water Lily, which like really emphasizes simple, fast fluids. Oceanagons, which is great for climate sciences, oceanography. It's crazy how it's used for these like super heavyweight studies. And then I started to take a swing at it in my first year PhD with something I called Aquarium, where when I started, I had no background in CFD. It was just kind of spun out on my own. And then I was really surprised back then and still surprised now that how I was able to cook up kind of an incompressible Navier-Stokes solver. And kind of what I'm going to talk about here is kind of follow-up to that, where even though Aquarium I thought was great, it was still had a lot of limitations, primarily because I didn't know what I was doing at the time. And one of those things is that it wasn't really multi-physics, in that you had to provide it pre-specified kinematics, as in if I have a foil bobbing up and down, I have to literally provide the trajectory, the full state trajectory, then I can feed it into my fluid dynamics solver, simulate the next time step, and what comes out is the actual simulator. So it's not really multi-physics in the sense I'm not combining the robot dynamics. And 4 years later, we finally figured out how to do that, in that we really looked at it from first principles. So the reason why this was hard is that because on the right, we have this incompressible Navier-Stokes equation. It's a PDE, we all know it, or have heard of it. It has nasty convective term, noblas, triangles, whatnot. And the difficulty here was, how do I couple this to the manipulator equation that we're really familiar with in rigid body dynamics? And this is usually where other simulators operate, right? Usually other simulators operate in this realm of PDEs and coupling, coming with ad hoc coupling forces. And what we did was, what if we look at a higher level and where it's really unified, and what comes out is this unified optimization problem that has all these very distinct principles baked into a single problem, where I can write down the Lagrangian for my fluid, for my robot, virtual work terms from external forces, and what really enforces coupling is the constraint, where if I write down things like conservation mass, conservation properties I care about, and things like no slip condition, that coupling term is actually what shows up in my force terms, where it's the same dual variable, and the Jacobian mapping is actually what maps it to each respective equation. And so this is a nice theoretical nugget, but what we asked ourselves was, well, if this unified least action thing really is what unifies everything, why don't I just discretize that problem directly instead of working with the PDEs and stuff? Yeah, sorry, I'm having some PowerPoint troubles. Things are auto-starting. And so that's exactly what we did. So we took this optimization problem and just discretized that directly, where I now have discrete terms for my fluid and my robot, as well as my external forces, and I still have all the conservation properties I care about, like conservation of mass, joint constraints for my robots, if I'm doing things in maximal coordinates, which is what solvers like Mujoko do, and I still have this coupling constraint. And the way I simulate this is by just deriving the first order necessary conditions like I would in numerical optimization, and then what pops out is an implicit time integration scheme, effectively. So I talked a lot about the physics, but I never actually talked about how the coupling happens. And so here we leveraged part of work called the immersed boundary method. So I'm just gonna go through this quickly. So the immersed boundary method is really nice for fluid structure interaction because the mesh of the robot and the fluid are separate. And the no slipping condition effectively enforces the velocity to be same at the robot boundary. And this is just to prevent fluid from penetrating a solid. And this is enforced by a convolutional kernel that maps the two. And this is parameterized by things like your robot configuration, the shape, etc. Though there is an issue with the original immersed boundary method, which is that it really only enforces this constraint at the nodes. And so there's nothing enforcing constraint in between the mesh points. And this can lead to things like fluid penetration and singularities. And so what we did was we came up with an integral form that essentially says, instead of looking at the nodes, what if I interpolate between them using linear segments? And then I can write down this term, this expression in an integral form, use a quadrature rule to discretize it. And what we see that is that at fine fidelities, these two methods both do a good job at creating a wake in a free stream condition. But if I coarsen the robot mesh, just the robot mesh, we see that the original immersed boundary cannot enforce no slip, but the integral form can. So fluid penetrates in the original, the integral form, as you can see, preserves the wake. So this is robotics. So we actually want to sort out a robot problem. So what we did was we actually recreated an EO robot setup on hardware and tracked it with a camera. And we actually evaluated an actual EO robot swimming. So Aquarium 2.0 is actually able to simulate a steady undulatory swimming motion. Meanwhile, Genesis, which is a multi-purpose robotic simulator, kind of just stays there. And we think it's because of the particle-based representation that these robotic simulators like to use. And of course, we wanted to try something crazier, an actual robotics task. So we tasked the simulator with optimizing what's called a C-start escape maneuver, which is a predatory evasion maneuver executed by fish. And the way we parameterized the problem was we asked ourselves, is there a way to control the direction of which it turns? So we wrote down a trajectory optimization problem to do this. And we use a simulator to pass its gradients back to the optimizer. And the initial guess we provided it was kind of this, we wanted it to achieve a 90-degree turn, and we gave it kind of a force from the initial guess. But after an LBFGS optimization run, it was able to achieve a 90-degree turn, and we're able to actually see this on hardware. And meanwhile, Genesis kind of still gets stuck. Yeah, and so future work, I would love for people to start using this, and for things like output feedback, pressure sensor simulation, and design optimization, and extending this to 3D. I think this is where the Julia community can really help out here. And in summary, so this is a unified multi-physics simulator for swimming robots where the constraints define the coupling. And we've successfully realized this on a bio-inspired swimming robot. Here's a QR code to the paper that we presented at RSS and the actual package for the simulator. All right, thank you. Yeah, so that's a nice part about the immersed boundary method is that for the fluid discretization, we just use a grid-based finite volume method, and it's 2D center difference scheme, like straight from the textbook. Yeah, that's a nice part about immersed boundary method. No matter how complicated your solid geometry is, it's the fluid discretization can be the same. Yeah, and that's the really nice part about it. Yeah, should I go? Yeah, I would love to. Yeah, I would love to look into this, like more turbulent flow regimes. But no, we just did like direct numerical simulation. Yeah, no turbulence model, no Smagorinsky, large eddies. Yeah, no, you definitely could. I'm actually interested in this because like, I think the recent trend is kind of this thing called implicit LES, which is like, kind of says like, so regular LES says I have to add like a damping model to damp out high frequency terms. Implicit LES literally says like, let the direct numerical discretization handle it, because some exist like third order upwinding schemes can actually handle. Yeah, for this one, I used like very coarse 200, like not super coarse, but reasonable. Like the EO robot was a 200 by 200 grid. Catch, yeah, exactly. Yeah, for sure. And I think in the swimming robot case, we care more about those macro level eddies.
Okay, so it's about time, so thank you.
Yeah, sorry.
Okay. Thank you. Let's thank you for your attention. Yes.
Test. Okay. Oh. But there's a problem. Ah. Okay. I don't know, it just worked. Like, is there a bad contact or so? I just tested it before. Let's see, let's try again. Otherwise, this USB-C. Okay, let's try this. So there was the.
Yeah, probably.
I see. let's try USB-C.
Yeah. Yeah, just correct this one.
Okay.
Okay, next speaker is Lucas Hub, and he's telling about HuBody Toolkit to Jail. Please start.
Okay, yeah, thank you and welcome to my talk. Thanks for attending, everyone. I would also like to thank the organizers of JuliaCon and also of this mini symposium for having me.
talk. And the next speaker is Ho Shao, and he's telling about implementing lattice QCD to multi-GPU system with Julia QCD.
Hello,
Please
okay.
start.
Yeah, my name is Ho Xiao, and I'm from University of Tsukuba, and thank you for the introduction and everyone for attending this mini symposium. So yeah, so like I'm using this Julia QCD. I'm one of the main user, and then the developer are here, like Tomiya and Nagai. So yeah, I will basically introduce how we do this multi-GPU computations for these lattice QCD computations. And then this is the outline of my talk. I will very, very briefly introduce you our scientific motivations, and then just show you some of the features we had for this Julia QCD package, and then explain how lattice people do parallelizations, and in particular how we do it in this Julia package. And then I show you some of the benchmark of our package that to do the parallelisms, and then it's the summary and outlook. So let me start from the motivation. So our motivations is the fundamental particle physics. So as everyone knows, this is the periodic table. And then inside all the elements, we have this atom. And then we are interested in the particle inside the atoms, which is called quarks. And then they are different colors, but no special meaning. But anyway, like all the physical objects that has to be color neutral. So the QCD stands for quantum chromodynamics, and then chromo means color in Greek. So this is the physics that we want to study. And then for this theory, it's a strongly coupled theory, so we cannot do perturbative calculations. We need to do numerical computations. So then we have to use lattice field theory to do the computations, and then we put on our physics or our theory onto the lattice, and then we generate some configurations that is following some certain distributions of our physics. Then we do the measurements of some physical quantity, and eventually, this is one of the example I show from a group, B&W group. They measure the spectrum of these particles. As you can see, they are well matched to the experimental discovery. So this is the basic idea of what we are doing. So for the computational task, because we discretize our theory onto the lattice, and to have like very precise physical computations, we normally need like 10 to the 7 or 10 to the 9 this kind of lattice sites. And then for each sites or each links, we put on our gauge field, or you can think of the force mediator of the strong force that is sitting on the links, and then you can interact with the matter field, the fermionic field, the quark fields we have. And then for these gauge links and also for these matter fields, they need to satisfy their physical feature. So currently, physicists think that they are satisfying this gauge symmetry, which is SU3. And then in terms of their matrix structure, they have 18 complex numbers. 9 complex numbers, so 18 numbers, sorry for the typo. And then, yeah, because we also carry the color of each quarks and also their spin indices. So for a fermionic field, we have these 12 numbers. So totally, the memory need or the computations we are taking is around this scale, like very large, already gigabyte scale. So this is kind of the numerical challenge. And on the other hand, because we want to probe our theory to the physical regime, so like in terms of this theoretical challenge, it's also very difficult if we have more flavors of our fermion, or like when we simulate in a very light quark, the simulation also slows down. And also we need to reduce the discretization effect, so we need to simulate a large enough lattice with a small enough lattice spacing to reduce these discretized artifacts that can reach to the precision computation of your physics observables. So these are like very expensive computations. So yeah, on the one hand, we need large memory demand, and then also it's a like very heavy computation, so we need to use HPC. So that's why we initiate this package to using Julia. And then, as everyone say in this conference, like Julia is very easy to code, and then particularly we are interested in using Jack, that it's like portable for all the HPC, because our goal is to simulate our theory on HPC, or we have to. And then currently, like each research institute, they have very different HPC. So we want to write a code that can work on all the HPC. So we pick Julia and then working with this Jack package. So currently already test our package or this software on Intel GPU and also NVIDIA and also AMD and also on this Mac. I also can run it with Metal with single precisions. So this is one of the benefit or one of the goal that we want to use Julia to simulate our, to write our software. And then some particular features we can use is also this auto differentiation. Yeah, so Nagai-san will talk about this later. And then, yeah, like there are several talks in this session that are also related to this package. Then if you stay tuned, you can see their talks. So yeah, so speaking back to lattice, so once we generate this lattice and then use some simulation to generate the configuration that satisfied to our physics distributions, then we can measure some physics quantity. But still, we have some lattice spacing dependence, so we need to do some extrapolation to remove this. However, this is the basic idea. We have one lattice, and then we want to measure something on our lattice. However, this is very expensive. We cannot simulate this large lattice on a single node or your laptop. So we divided them into some small sublattice so that we can compute all the sites at at the same time. And also we can reducing the memory requirement per node. But these will introduce this communication challenge to our software development. So the way we do this communication is that we divide it into this small sublattice. At the same time, we extend the links to its neighboring link, so they share the same link, so we don't need to communicate with sublattice. We only update the link once some operation was done to some sublattice. So this is the idea that we can reduce the communication between sublattice or between nodes or between cores. So we have this sublattice, and then we have this hello space that is like redundant links, sharing the same link of your neighboring sites. Then we can put on these small blocks or these small sublattice, including the hello space on some processors or node. Then some MPI, like taking the responsibility of your communications. Then by doing all this like repeating, or you can divide it into some small different number of sublattice. Then eventually, if we want to compute some global quantity, so global means like the whole original whole lattice, we use MPI like O-reduce to get informations. And in terms of the development of computers or our machines, in the beginning we have these CPU chips or CPU processors that you need to go through all the sides of your lattice, but you can do it at the same time with multiple processors. So this already can speed up your computations. But recently, people already have this GPU, so we can use GPU accelerate to compute the same thing at the same time, but still, in the beginning, we don't have direct communication between GPUs, but currently, the latest technique is that we can already do some direct communication between GPUs. So these also speed up our computations and then can reduce the communication time. So later, I will show you some of the benchmark we did for this software. It's already showing the results with these direct GPU communications. I put a star here, it's because it really depending on your machine. So you need to set up a correct environment, or you have to check whether your machine can do these direct communications. Yeah, so now I would like to show you some of the benchmark we do. Particularly, we focus on the parallel efficiency, and then I will show you one by one. So for the simplest test is doing these Pluckett computations. So Pluckett is the multiplication of our matrix, SU3 matrix, 4 times or like 3 times together, and then form we call it a Pluckett, like 4 links of this, and then we sum over all the sides. So as you can see, this computation can be done parallelly. So we can do this at the same time for each side at the same time, and then sum over all of them, and then we get the global quantity of this whole lattice. So can you see? You cannot see, okay. So yeah, on the right-hand side, this is the computational nodes with different lattice size. So the blue one is 48 to the 4th lattice. And then for the red one over there is the 128 to the 4th. So this is already like very large computations, but because Pluckhead, it's a kind of simple computation, and it's good for do the benchmarking. So on the y-axis is the wall time to compute these Pluckhead values in milliseconds. And then here I check the change of these lattice sites, and then with respect to different nodes. But what I wanted to show you here is these plots. So I checked the efficiency, which I used the like just one node, no parallelisms, used on GPU, and then divided by the wall times at different nodes times the number of nodes to see how good they are. And for the green one, like 96 to the 4th lattice, because the memory issue, I cannot run it with single nodes, so I normalized to 2 nodes. So this is kind of the parallelism efficiency we have. And then on these sites is like the computational cost per site with respect to the lattice size. So yeah, so we are still working on it to improve it, but I think above like 80% of your parallel efficiency is kind of acceptable, yeah. And so, but we are trying to push like more and also at the same time reduce the memory cost, yeah. So this is like an ongoing project, but already can do for mass productions, yeah. So this is the summary and outlook. I will just leave it here because of the time, and then thank you for your attention.
Okay, now time for question. Okay.
You probably mentioned this and I didn't quite pick it up. Did you use kernel abstractions for your...
No, we use Jack, so you can write the same kernel functions and then change the backend. It's the same as kernel abstract, but I think I'm not familiar with kernel abstract, but one thing is good for Jack is you can run with threads backend, so you can run on CPU. So when you're debugging, you can print out something to check. If you run on GPU, you print something, you explode. So I think this is one of the benefits using Jack.
I do think kernel abstractions does have that feature, but it might be a little bit different.
Yeah, I'm not familiar with that, but yeah.
Okay, cool, thank you.
Do you see any influence of cutting up your space into chunks and then not letting them communicate over some time? Like,
sorry, can you ask your question again?
You have a large space which every site communicates to its neighbors, except you cut some of them off to make it parallel. What is it? Do you see any influence of this on the final results?
No, they should be exactly the same. Only up to some machine precision. So so basically, like when we cut our lattice in many different ways, the results are compatible or up to machine precisions. There's no difference. Yeah. But in terms of efficiency, if you cut in the same directions or the outer rim of your for loop, it's faster. Yeah. That's the only difference we see. Yeah.
I think there's time for one more question. Cool, thanks.
Okay, thank you.
Okay. Yeah, we will list 45. Yeah, 45. Yeah, something wrong with this one, right? So this should be starting from 40. coffee break. Well, yeah, this really overlapping. The other talk will start from 45. So that should start from 45, right? Yeah. Maybe I should ask the organizer about that. Hey, can I ask that? So I think this is something wrong.
I think so as well.
Okay.
I don't know, but I mean,
Maybe.
it says coffee and cake.
Yeah, right. This is.
I think we should do
Oh, yeah, we should. Yeah, okay.
but
Maybe I should announce
just
that.
noticed it as
Yeah.
well.
The program on the something wrong. We restart from 45 after the coffee break.
So, welcome back from the break, and let's begin the next talk on lattice QCD. Please begin, if the mic is working. Let's see.
Hello? Can you hear me? Okay. 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 Wait. What happened? What? Okay. Yeah. Okay. Thank you for coming. I'm Yuki Nagai from the University of Tokyo in Japan. And today I'm talking about the Julia QCD project, which is a pure Julia framework for lattice QCD, and I would like to talk about its extension with compiler-level automatic differentiation. My interest is that how fast is Julia? Usually, Fortran and C++ code is very fastest, I think, on supercomputers. So, but as you might know, the Julia is fast as Fortran and easy as Python. So how fast? So we are developing the Julia QCD code on supercomputers. Actually, I'm a condensed matter theorist, so this means that Julia QCD, the quantum chrome dynamics is for high-energy physicists. So, but with use of Julia, we can collaborate with high-energy physicists. And actually, I wrote 2 books, but unfortunately, these are written in Japanese. Okay, so this is outline. First, I'd like to introduce lattice quantum chrome dynamics, which is high-energy theory calculations. And I would like to introduce jack.jl. Usually nowadays, there are many kinds of the GPU hardware on supercomputers. For example, in Japan, there is a GPU supercomputers. In US, United States, there are AMD GPUs. So this means that if hardware is different, it looks like we have to write different code for different architecture. But this is very time-consuming to write the code. So with use of Jack, we can use one code for different hardware. So we implement jack.jl to our Julia QCD code. And I also introduced a general method on lattice. This is the lattice matrices.jl. And also, with use of enzyme.jl, we introduced the differentiable lattice quantum chrome dynamics. Enzyme is very useful and interesting because we can obtain the derivative of the observables. And enzyme uses the LMVM level derivation of the derivative of the observables, variables. So finally, the benchmarks and summary are given. So first, I'd like to introduce the lattice QCD, but the previous speaker introduced this. But for me, I am a condensed matter theorist, so usually I introduce the periodic table of the elements, and there is a hydrogen, and inside hydrogen there are proton and electron, and inside the proton there are quarks. So the QCD is a quantum chrome dynamics, and this is a fundamental theory for particles inside of nucleides. So this system is quantum many-body and relativistic and strongly correlated system. So I think this is one of the hardest problems in the world. And to treat quantum chrome dynamics, usually we use the lattice. Universe is usually everything is defined on the 3-dimensional space and 1-dimensional time. So usually we have to consider the 4-dimensional space-time. But of course, space and time is continuous, so we have to discretize this space and time in the computers. So we introduced the 4-dimensional lattice like this, and gluons and quarks are defined on this 4-dimensional lattice. And we have to do the Monte Carlo simulation to obtain the observables, which is observed by the experiment. And what kind of calculation is needed? The most time-consuming part is solving linear equations. And the number of the linear equation is, for example, in this case, 100 times 1 billion steps. And the matrix size of this is, for example, 10 million. So this means that, of course, this is sparse matrix, but this is time-consuming. So usually we use supercomputers. So conventionally, we have used C++ or Fortran with massive parallelization, for example, with MPI or OpenMP or GPU or hybrid of these on supercomputers. Because as I said, this is one of the hardest problems in the world. So usually we have to optimize the code. So usually we used the C++ or Fortran. But as I said, Julia is fast as Fortran. So if we write code written in Julia, what happens? So this was my motivation. So we made a code written in Julia. And as I said, lattice QCD is one of the most numerically expensive calculations, and also this is very useful to understand our world, of course, and this becomes a good benchmark of software or hardware. So, and there are many public codes for lattice QCD, and many codes are written in C or C++ or Fortran. Sometimes this written in assembler. So this JuliaQCD is our project and written in Julia. And as I said, we need highly optimized code for lattice QCD calculation on supercomputers. So the C++ or Fortran is a good choice because this has a long history on supercomputers. Now we made lattice QCD code with Julia because it is easy to use. It can work on PC and supercomputers, even on the Raspberry Pi, without any change. So we use Julia. And as I said, the benchmark test is very important because lattice QCD is one of the realistic applications of Julia. So we try to make the lattice QCD code in Julia. And also, important point is that we want to minimize time or effort for code development and execution. So we developed the lattice QCD code for generic purpose, and this is latticeqcd.jl. And this is very easy for beginners who studies quantum chromodynamics. Usually, and of course there are many good softwares, but sometimes it is difficult to compile it. So with use of latticeqcd.jl, we can start easily, I think. And this is package structure. And now we have a JuliaQCD project which have several packages. For example, the gauge field is a package that treats gauge field on lattice, and lattice-Dirac operators which treats fermions on lattice. So there are several packages. And the important point is that we can easily use this package. Of course, this is a Julia package. So why do we use Julia? As I said, Julia is fast as Fortran, and it is easy as Python. So as I said, in lattice quantum chromodynamics, we have to solve the large linear equation many times. So this is very hard and time-consuming task. So usually, we have to have highly optimized code. But the highly optimized code sometimes means the compiling it is very difficult. For example, if we use C++, we have to introduce some kinds of other additional packages. Of course, in Fortran, we have to introduce other packages. And sometimes, if we consider some, for example, the Fujitsu CPUs, we have to write a special option to optimize the code, to compile the code. So this is sometimes this is very difficult. In my opinion, when I tried to use the C++ package, but I failed to do it because I could not compile the code. I think it takes 1 week, but finally I gave up. Okay, so with use of Julia, we can easily use this, and this means that this code has a portability. So the latticeqcd.jl works even on Raspberry Pi 02. And it is easy to understand. As you know, the Julia is easy to understand. I think syntax is easy, I think. And also, this is machine learning friendly. And usually, many machine learning code are written in Python, and also in Julia, there are good packages like flux.jl and lux.jl. So we can easily implement the machine learning technique to the code. But if we use C++ or Fortran, I think this is very hard. I try to use this, but sometimes we have to write the MLP much layer perceptrons in Fortran. Of course, we can do it, but it's time consuming. So with use of Julia, we can easily use a machine learning technique. And I'd like to note that Julia uses LLVM. So I think, as you know, there are many languages, and all language, I think nowadays there are many languages which use LLVM, but this is an intermediate language, and finally we obtained the machine code with use of LLVM. So we do not have to write different code for different CPU architectures now. And I would like to show the comparison between the Fortran code and Julia code. This is time, elapsed time, as a function of the system size. And we tested the Fortran code, but this is old code. I think this is called lattice toolkit. And this graph means that the Fortran code is slower than Julia code. So this means that Julia code is faster than the Fortran. So I was very happy. But I have to note that we did not compare with cutting-edge packages like Milk, Grid, Bridge++ written by C++. I think this was developed, I mean that Lattice Toolkit was developed in 2002 or before this. And I think, I don't know, but this is just a Fortran code. So I think there is no highly optimized techniques. So if we try to use, try to do the benchmark test with Milk and Grid, Bridge++, maybe these are faster than our code. So we have to optimize the code. But anyway, if we compare the Fortran code, we can have a faster code written in Julia. And I would actually show the MPI performance. And with use of the supercomputer, the Wisteria BDX01 in the University of Tokyo, we can get good scaling well. It looks scaling well. We change the number of the MPI processors, and this is Julia, so we can easily use MPI. And also, I'd like to show the CUDA performance. Now Julia QCD can use CUDA. CUDA is a GPU computing framework, so I could implement CUDA version within 1 week without AI. So this is very important. By hand, it takes only 1 week. So this means that Julia is very easy to understand, and we can add additional functional. For example, in this case, we want to add CUDA functionality. But there are two bars. So this result is coming from with H100, and this is RTX 4090. These GPU are completely different. Usually, H100 is faster, I think. But in this case, there is more difference. So we have to improve the code. I don't know the reason. Because in this code, we just use CUDA.addSync. So maybe there might be more faster approaches. But now I don't know. So we try to use acceleration, and we try to use Jack.jl. So I'd like to introduce Jack.jl. But what should we do next? It is very hard to rewrite the code every time when a new architecture appears. So, okay, I wrote the code for NVIDIA GPUs with use of CUDA.jl. Of course, we can write the code for AMD GPUs. But what is the end? I mean, there are many hardware every year, I think. So, for example, in Japan, there is Fugaku Next, which has, I think, many NVIDIA GPUs. And also in the United States, supercomputers are using AMD GPUs. So should we write code for AMD GPUs? But it's not impossible, I think. But the important point is that maintenance. So maintaining hardware-dependent code is very difficult. So I think this is a common problem of the open source, I think. So we can easily add the code, but the maintenance becomes harder and harder. Okay? So we do not want to do such things. So now we try to use hardware-independent coding. In C++, there is a Cocos. Cocos can use OpenMP for CPU multithreading, and CUDA for NVIDIA GPUs, and HIP for AMD GPUs with one code. I think this is a very good idea. So in Julia, there is a Jack.jl. So if we use Jack.jl, we can do parallel computation like Cocos in C++. And I'd like to say that in Julia, we can run on different CPUs with use of LLVM, and with use of Jack.jl, we can run on different accelerators. And this is not our result. So this is just a developer's slide. So with use of Jack, with one same code, they can speed up the code. So this is a Threads case, NVIDIA GPU, M GPU, and also Intel GPU with one same code. So I think this is very useful and important. So we implemented the jack.jl to our code, and this is benchmarks. So this let is a single CPU case, and we can speed up the simulations like this. Okay. Next, I'd like to talk about the general method on Lattice. So we made new general packages, lattice matrices.jl. Because as I said, everything is defined on Lattice. And there are several kinds of the physical particles, gluons, quarks. And in lattice QCD.jl, we use, for example, 6-dimensional array for gluons, because the gluons are defined as a SUN matrix defined on Lattice. And quarks are regarded as n-time energy matrix defined on Lattice. So both two are represented by the 6-dimensional arrays. So it looks similar. So, and also, operations are similar. So we need matrix-matrix multiplication on each lattice, and also we need 4-dimensional state operations, because this is a 4-dimensional lattice. And we want to do the parallel calculations with use of CPU or GPUs. For example, as I said, there are many kinds of GPUs now, NVIDIA, AMD, and Intel GPU. And also, we want to use merge GPUs on supercomputers. So now we combine the MPI and jack.jl. And also, we have to write the backend package, because as I said, if we have many codes, the maintenance becomes very difficult. So we made lattice matrices.jl, and we use jack.jl as a backend, and we use MPI for the domain decomposition. And our code can run on CPUs, NVIDIA, AMD, and also Intel GPUs, and also my GPU clusters. And this is designed for lattice local operations. So I think with use of this, we can treat the quarks and also gluons. And we can easily add new functionalities on this software. Then we can use new functionality for the gluons and quarks. So now we try to implement the automatic differentiation. Okay. So in this field, in lattice QCD field, usually we use analytic differentiation. And in simulation, we have to do the HMC. HMC is the Hamiltonian or Hybrid Monte Carlo. So usually we have to do the molecular dynamics. So we need force. So force is defined by the derivative of the action. And so we have to have a derivative of something. But usually the action is complicated sometimes. So force is derived by hand, but it's time-consuming. And sometimes there is a complicated action, then we have to derive the forces, then we can write a paper, for example. But anyway, nowadays, there are many machine learning techniques. One of these is automatic differentiation. So with the use of the automatic differentiation, maybe we can derive the force. But why AD? I mean that in lattice QCD, AD is difficult. There are several reasons. One is the complex valued variables. We have to derive the derivative of the action, and the variable is complex. And also, this is matrix. And also, important point is that there are many in-place operations. Then maybe you know that if we consider the machine learning model, we have to have the derivative of something. Then, in this case, we make a graph to get the derivative. But if there is some in-place operations, we cannot make a graph, computational graph, because this is a 6-dimensional array. Variables is on the 6-dimensional array, so which means that we have to avoid to make the new arrays, because it has much memory. So usually we use the in-place operations. But with use of the in-place operation, I think that it is very hard to derive the derivative of the functions. So usually if we use the PyTorch or JAX, it is very hard to use it. Of course, I know we can do this, we can do with use of PyTorch or JAX, but I think that we need much memories. So now we focus on LLVM, because Julia is based on LLVM. And LLVM has a good properties. Well, for example, the LLVM IR, intermediate representation, is expressed in the static single sign assignment, SSA form. This means that each intermediate value is defined exactly once, even if there are in-place operations, which means that we can easily track the operations. Then we can define the derivative of the action. And with use of enzyme.jl, we can do it. So now we use enzyme.jl as a backend, and we have to define the custom adjoint of the enzyme. For example, we need a matrix operation on the lattice. So this is a primary calculations. And now we are using jag.jl on the lattice. And also, the adjoint of B or adjoint of C are defined like this. This is very similar to the primer. So this means that we can use the jag.jl. So we write the custom adjoint of for the differentiations. So with use of MPI and jag.jl and enzyme.jl, we can have the automatic differentiation on the lattice. So I'd like to show the benchmarks. First, this is accuracy. The important point is that LLVM level automatic differentiation is consistent with, of course, handwritten implementation. And we have good physical scaling. And the important point is the wall clock time, I think. This is there to code, handwritten code, LLVM AD code. And it takes, for example, with the use of the handwritten code, this is 195 seconds with use of one CPU core. And with use of LLVM, it takes, for example, 162 seconds. It is faster than original calculations, for example. And with use of the H100, we speed up simulations. Then, for example, with use of LLVM AD, it takes 3.39 seconds. So with use of MPI.jl and jag.jl and also enzyme.jl, we can speed up simulation and we can have automatic differentiation with in-place operations. And I would like to note that this means that LLVM AD is always faster than handwritten code. I mean that in this case, LLVM AD code is faster than the original code, but I think that this means that the speed is comparable. Finally, the summary. Quantum dynamics has been simulated on supercomputers. So my interest is how fast is Julia. So we developed the lattice QCD code written in Julia. And now we made new backend lattice, so-called lattice matrix.jl. And now we can treat gluon and quarks with GPUs on lattice. And also we provide LLVM level automatic differentiation in quantum dynamics. And thanks to jag.jl and MPI.jl and also enzyme.jl, we can make a code which has a good speed on supercomputers. Thank you for attention.
Thank you. Any questions?
Yeah, thanks for the nice talk. So in the written algorithm and your enzyme, is it the memory cost largely different between these two implementations? The speed is good, but what about memory? Is it still okay?
Memory allocation, I think it's similar.
Similar?
Yeah, because these both use in-place operations. Of course, we need more additional arrays, but it's not so large, I think.
I see, I see. Okay, yeah.
Any other questions? Nope. Thank you.
Thank you.
wait 5 minutes. Right, let's start the next talk. Oh, you need the mic.
Can you hear me? Oh, okay. Yeah, thank you for introduction. So, hello everyone. So I'm Kento Shimura, a PhD student coming from Tokyo. So in the first place, I would like to appreciate organizers for providing me this opportunity and also giving me this nice t-shirt. So I'm now engaged in the research project of physics using Julia language, and in this presentation, I want to talk about it. The title is Parameter Optimization of Domain Model Fermion based on machine learning framework, and the collaborators are these three people. So let me start. So as Shao-san said, the QCD is one of the most fundamental theory in the theoretical physics, and the lattice QCD is a formulation of the QCD defined on the lattice sites. So one of the important concepts of the QCD is the chiral symmetry. So this is, to say very roughly, it is a reflection symmetry of the particle and the particle motion. So this should be satisfied in theory of the QCD. However, in the lattice QCD, to satisfy this chiral symmetry strictly, there is a fermion doubling problem where some unexpected contribution changes the result of the calculation. So this is why the widely used is this Wilson-Dirac fermion, so which is this formula, and this term apparently breaks the chiral symmetry. However, in the continuum limit, the violation terms vanishes, so and it is very convenient and it is very widely used in the field of the lattice QCD. On the other hand, there's another way to recover the chiral symmetry in the lattice QCD. So this is the domain model fermion. So in the normal lattice QCD formalism, there are 3 space and 1 time. So this is why the 4-dimensional space. So in the domain model fermion, we assume the additional 5-dimensional space like this. And by imposing appropriate boundary condition, we have a clock with satisfying the chiral symmetry, but approximately. The indicator of the chiral symmetry is this residual mass, or m-res. So the smaller m-res means a good chiral symmetry. And one of the ways to improve the chiral symmetry is to get larger the 5-dimensional length, so 5D length. So as the length gets larger, the m-res decreases. So this means the chiral symmetry improved. And on the other way to improve the chiral symmetry is changing the parameters in the domain model fermion. So actually, domain model fermion can have 3 parameters like this. So this maybe is domain model fermion, and in general, domain model fermion has 3 free parameters at each 5-dimensional slice. And it is known that by changing the parameters, we can improve the chiral symmetry without getting larger 5-dimensional length. So this is a sequence of the m-res by a function of this p. So, and our idea is to apply the machine learning framework to this domain model fermion and optimization of the free parameters. So this is a brief framework of the machine learning. So we assume that some parameters and the loss function as a function of this parameter theta. And by using this, we can get a gradient of the loss function, and by iterating the gradient method, we can have an optimized loss function like this. So this is a framework scheme of the calculation, and in the lattice QCD calculation, we need to calculate the HMC, a hybrid Monte Carlo step. So this is very computationally demanding. And also, for getting the loss function as a minimum, we have to calculate this m-res. So this is also very demanding high computational cost with a stochastic method like this. So this is a framework of our calculation. And this is a computational step in detail, but you don't need to read them. So although Nagai-san said everything, and we use the Julia QCD package written in the Julia language. So in the Julia language, in the current situation of Julia language, it provides standard functions in some HMC calculation and something. But in the domain model fermion, the machine learning is now experimental functions, and our work is to developing this code. And also for GP acceleration with the Jack package, as Nagai-san said. So this is how to develop the calculation code. So in the first place, we write a LaTeX node which contains the formulas we use. And also we have a basic code in JuliaQCD. And I ask the Claude write a code based on this node, and the Claude write a code. And also extend it to GPU acceleration, and we have to only test, write a test code and check the result and the code structure and like this. So this is a GPU acceleration process. So in the original JuliaQCD package, so there is some memory allocation problem and some kind of consuming memory in any place in the domain-evolved fermion code. And we improved this memory allocation using the organizing acceleration kernel of the domain fermion and also mixed precision solver and like this. And all of these process is done by the LLM like this. And by doing this, we can accelerate the calculation code by 8 times or 9 times speed up. So this is why we can perform the calculation in 1 day for some complete calculations. So what time is remaining?
You spend 6 minutes.
6 minutes? I spent 6 minutes. Yeah, okay. So this is the calculation result. So this is a sequence of parameters as a function of the trajectory. So as you can see, the parameters goes to some point, and there's some fluctuate in the around the convergence point. And also we can see the trajectory of the loss function like this. And there's some very fluctuate, but it is because the M-res goes around the 0, positive and negative like this. So this is why at the convergence point, the loss function very fluctuates. So however, we can get the convergence solution of the B parameter and the C parameter like this. And this is also verification of the calculation. So we take the parameter sets of the 100 trajectory and 200 trajectory and so on. And by using these parameters, we restart the calculation of the HMC and get the physical quantity in the stochastic method. So this is the calculation result, and we can see as a step process, the physical quantity of the residual mass goes down. So this is why we can say by using the machine learning, we can reduce the residual mass without getting larger 5-dimensional length. Well, this is a summary of the calculation, presentation. So we developed the calculation code for domain-evolved fermion using the machine learning with the Julia language. So in the Julia language, in my opinion, this is very promising framework where because it is very fast and readable and also compatible with the GPU and the machine learning framework. So I expect that this Julia language will become a standard calculation language in computational physics field. So it's some time remaining, but that's all. Thank you.
Thank you. Any questions?
Do you have some tips to ask to Claude?
Yes.
So can you tell me?
How
do you have some tips?
How to say? So I think it is important to prepare a LaTeX node in a text, not PDF or something. just it.
Any other questions?
So yeah, you show that your speed up like to 9 or 8.
Yes.
I also noticed that this is quite interesting in Julia. When you change something, the speed up is really fast.
Mm-hmm.
What did you change in this case? Do you remember?
So it is just because domain-evolved fermion functions are very experimental. So for example, in the domain-evolved fermion code, there's some, consuming a memory allocation. For example, some temporary field also have a temporary field and something. So in the first place, we reduced all of them. And also, as written in the slide, we prepare some acceleration kernel of the domain fermion using JAG. So this is all of our work.
Any, yep.
Thank you very much for the nice talk. I actually also had a question about how you used Claude. And I mean, did you find some particular difficulties in making it understand? Like, did you already have some code to start with to feed to Claude so that it would understand how you wanted? Or did you really use it like you wrote in the meme, like, please write this code for me? And if so, what were the difficult part of doing this? Because I'm interested in.
So excuse me, what is the question?
What were the difficult parts of using Claude to make it understand what you wanted to do in the end?
How to say, it is difficult to say. But so, in this case, we in the first place, we have some basic code, and so it is difficult to get Claude and write a code which is compatible with the package. So in the first place of the development, so there are many errors of the functions and like this. But in the Julia code, the stack trace is very readable, and the origin of the error is very clear. So this is why it is very easy to repair it.
Okay, I see. Thank you very much.
Cool. Any other questions? Thank you.
Thank you.
Take a picture. Let's begin the next talk by Shohei Ono and myself. Please begin.
Thank you for introduction. I am Shuhei Ono from Japan, and I'm an organizer of this mini symposium. Thank you for attending to this mini symposium. Last JuliaCon, I attended last JuliaCon, but there is not computational physics mini symposium. So I'm really happy to hold this mini symposium. Okay, today I would like to talk about testability first design for free-body systems physics. The main topic is design, software design. So this is a general introduction of computational physics mini symposium. Why computational? The answer is here. So too complicated to solve. And so we need approximate practical method. So this is a word by Dirac about 100 years ago. So we are developing the practical method. But there is no perfect method. So we should choose the methods to each problems. And I have a vision in the computational physics. My field is free-body systems physics. This field is have been working as a trading port of numerical method in physics and chemistry. But currently, there was not open source software. But so we need to collaborate and trade the method. And the user-friendly and flexible and portable open source software is needed to share the method and to use to other field. And I want to introduce the free-body systems physics. What is free-body systems physics? Typically, the free-body systems physics is solving the Schrödinger equation for the systems of few particle. What's few particle mean? The example, this is a helium atom. It is made up of one alpha particle and two electrons. It's three-body systems. And so, as you know, the proton is made up of three quarks, and the alpha particle is made up of two protons and two neutrons. And the helium, as you know, this is a nucleus of helium atom, and the atoms make molecule. And so there are so many kinds of systems. So there is no perfect packages. There's no packages for cover the orbital particle numbers and the interactions and the quantum state. So the researchers build self-tailored code bases. So, but a few years ago, one open source was released. This is atom more non-bio for atom and molecules. And after that, micro researcher Martin Mikkelsen releases this free-body physics JL. And a little later, I released the two-body JL. This is a general package for two-body problems. We can customize the interaction between two particles. And currently, the presentation by Lucas Happ, the few-body toolkit can cover the two-body and three-body and any kind of interactions. And our goal is few-body JL for orbital particle numbers and interactions. And so we need to learn the Hamiltonian of free-body system physics. What is interaction? We solve the Schrödinger equation with this Hamiltonian. We want to get the eigenfunction and eigenvalue of this operator. This is a Hamiltonian of hydrogen atom. It's there are two particles, so there is one kinetic term and one more connect to the second kinetic term, and this is the Coulomb interaction. In the meson, in the very smaller than the smaller scale, in the smaller scale, there are the kinetic terms, and there is very complicated interactions. So we should change this term, this interaction term. And in the three-body systems, there are three kinetic terms and three interaction terms. And in the four-body system, there are four kinetic terms and maybe 12 interaction terms. Six interaction terms. So from this table, so we want to customize. We want to change the number of kinetic terms and the interaction, then the function form, and we want to change the function form of the interaction. So this is the free-body systems have very simple Hamiltonians, but various interactions and need flexible Hamiltonian structure. So we launched the Julia free body, and you can find this our organization in the website on Julia website. And our goal is complete the free body gel that is open source and open formula and any number of particles, any interaction, and several methods. So please visit our website and give us stars for packages. Currently, there are more than 10 packages. And today, we would like to talk about two-body and free-body gel. But free-body gel is a little complicated and too large. So today, I mainly talk about two-body gel. This is a proof of concept of free-body gel. You can find two-body gel on our repository here. And this is very simple package, only for two-body systems. So I wanted to talk about what we are implementing. This is one of the methods for free-body systems physics, Rayleigh-Ritz variational method. So we must calculate this equation by hand to solve this Schrödinger equation. So we use basis set expansion approximation, and we generate this calculate the matrix elements and solve this generalized eigenvalue problem. The solver, the input of solver is the Hamiltonian and the matrix overlap matrix, and output is energy, eigenvalue, and eigenvector. From these values, we can get the energy and the wave function and any other physical expectation values. To implement this, we must calculate this one by hand and implement and code, implement this one, and using linear algebra, and we get this energy. The exact value is minus 0.5, so it's really good value. This is just a simple example of the Rayleigh-Ritz method. In our package, here is a solver function, and the input is Hamiltonian and the parameter of method. So we define the many solve functions by using multiple dispatch, and there is a part to calculate matrix element, to calculate matrix. And here is solving generalized eigenvalue problem and return some result. Very simple structure of function. And the usage, so the design of this package is very simple. So there are equation formula of Hamiltonian and the basis functions. And this is the code of two-body jail. So we define the Hamiltonian, one kinetic term and one Coulomb interaction. So there are two terms and there are two lines, almost the same. And there are four basis functions, and in our package, we can define the base function one line, and there are four lines. And we give this Hamiltonian and basis function to the solver. As a result, we can get the energy and the wave functions. It's really good, amazingly good for only four basis functions. You can find this word in the textbook by Thyssen. And also, you can find this example in our documentation. I think this is really nice, education material for students. So please visit our document. You can find more rich result. This is a result for not only for ground state. This is the excited state. They are node. And really good wave function and really good energy in the excited state. And also you can find many methods, Rayleigh-Ritz method and Gaussian expansion and free complement method and the finite difference method and QTT and tensor train, the tensor network method and the neural network method and Monte Carlo method. And there is a result of so many methods. And please see this value. Some method cannot calculate the excited state, but there are 1, 2, 3, 4 methods to calculate the excited state. So we can compare them and verify the result of the calculation. But be careful, it depends on the parameters. For example, the finite difference method depends on the grid point, number of grid points. And so we developed so many methods, but we don't need so many methods. Only 2 methods are necessary. There is a problem how to verify the result, how to do system testing. For system testing, we can use test oracles. For example, the exact solution of hydrogen atom or harmonic oscillator and any other systems that have analytical solutions or well-researched system. So we can use literature reference value for known problem. But how to test the different unknown problems? The answer is differential testing. Compare the result of 2 methods. So for unknown system, we cannot use database. We don't have analytical solution and any research paper. So we should verify by ourselves. In this case, we can use Rayleigh-Ritz method and finite difference method. We can compare their result. From these requirements, the software architecture is almost uniquely determined. So at first, we should develop the Hamiltonian the module to build Hamiltonian. And next, so we can make a database if there are literature values or analytical solutions. And this value, the database is very important to testing Rayleigh-Ritz method and finite difference method and any other method to test each method. After that, so we can compare these results for unknown systems. So this is architecture of two-body JL, and also we use this architecture for few-body JL. So currently, there are two methods in few-body JL. One is explicitly created Gaussian. It's one of our Rayleigh-Ritz method using explicitly created Gaussian basis functions. It's really highly accurate method in few-body systems physics. And Martin developed this package. And this is another method is variational Monte Carlo method. This is the method that trial, we can use any trial function in this method. And we evaluate the energy using the metropolis sampling. This method is really a little difficult to calculate the excited value, but we don't need to calculate the integration. So we can use any the arbitrary basis functions and trial wave function, for example, neural network and your favorite functions. So variational Monte Carlo method is not good for excited state, but very good to testing ground state. And this is the trial calculation. And here is the ECZ, explicitly created Gaussian, and variational Monte Carlo method and database. So we can compare these methods with database value. And a little higher than the database. But this is a very easy calculation on the documentation on GitHub. So we cannot use so much calculation computing resource. But if we increase the basis functions, we will get more accurate values. So this is, so I told strategy to design the architecture of software in two-body systems, and this is the current progress in the few-body JL. And so this is conclusion and acknowledgement. And today I talk about the few-body systems. What is few-body systems? The few-body systems physics. And I introduced Julia few-body packages, and especially two-body and few-body JL. And so talked about the development model. So you should develop the Hamiltonian, building Hamiltonian module and test Oracle database module. And after that, you can implement any solver you like, your favorite solver. And we need at least 2 solvers for differentiation testing for unknown system. And so we integrate these solvers in your package. So this is our development model. I think you can use in your field. So I want to say thank you for the RIKEN Junior Research Associate Program and the Travel Award for JuliaCon. And last year I supported by the APS and all sponsors through the GitHub sponsors, Yusuke Sato and President Shohei Takahashi and Director Shinoguchi. And all the donors of the Academy Prize, I'm coming here by their support. So Julia co-creator, Dr. Jeff Besançon, and my uncle Masaki Koizumi, and my father Hisashi Ono, and so many supporters. So I want to say thank you so much.
questions?
Thank you for a nice talk. And I have a question on the Oracle part. You mentioned to the making some database, right?
Database, yes.
Yes. And but how to say, some stochastic method depends on the random number.
Yes.
It is difficult to compare, basically.
Yeah, of course, there is no, there's error in the stochastic method, but we can define the, how to say,
so by database in this case, we mean like observables, so like actual measurements and so on. And we also have stochastic methods for like different methods and for different numbers and so on. So like a huge table of like, let's say 30 methods and examples and numbers and so on. Then we just have this huge table. Yeah, that answers your question.
Yeah, but if you implement some new method, so we want to compare the known result.
Yeah.
And the deterministic method is fine because the result is quite, how to say, should be same in the method decision. But for variational-based method, how to say, stochastic method, it depends on the random number.
Yeah. That's true. Yeah.
I mean, I want to know the strategy to.
Yeah, we can decide the acceptance range between the gap between the stochastic method and database values. So, for example, there are the 10% error or less.
And also, I mean, it is random in nature. Like it's based on sampling, so we have to like either crank up the numbers to some very high number, or do some smarter sampling. And we started out by doing like uniform sampling, which turned out to be not so nice. And then we moved on to like quasi-random sampling, which is much better. Then we have done like benchmarks for like different kinds of quasi-random samplers, like Halton sequences and so on, which is much nicer in this case. Yeah. Any other questions?
Yeah, it's not my field, so maybe the question is a bit naive, but it's like, what is actually like scientific question you are trying to solve? Like once you have simulated this like 2 or 3 body problems, what do you actually learn from like physically?
Sorry, I couldn't catch your question.
Like what are you actually trying to? What is the scientific question you are trying to solve by simulating these few body problems? Like, is there like what do we not know about molecules with 3 atoms? Like,
Yeah, so this is basically like a first proof of concept. And then like the next step could be like measuring scattering angles and so on, which is also possible like in this framework. So I mean, this is like a nice tool for scattering experiments and so on, which is not so much known in this case. 3 body particles, 4 body particles, some other particles. So basically scattering experiments in general.
Thank you. Yeah, maybe first as a comment to the previous question. Also, for one example would also be nuclear physics. They have some methods for calculating, or like efficient methods to calculate big nuclei of 100 particles, but they need input data, and there's not enough experiments to fulfill all their input data. So what they need is very accurate calculations of small-scale systems, which they can trust, because these methods then are again tested against, they need less input data, so we can trust this small-scale calculation or like these small particle systems, and then we can use not only experiments but also calculational data as input for other methods which are good for big systems but bad for small systems. That would be one example. In atomic systems, there's other questions, but I mean, I can tell you more later. I have actually also another...
Thank you for supporting.
Sorry, what?
Thank you for supporting.
I have also like another question. So you showed the example with 4 basis functions, and that is nice. So I think that was Gaussian basis. Do you also support other basis functions currently?
Yes. In this package, there is a... Can I see the documentation? Sorry, the unconnected. Okay, there's a free complement method by using the Slater type basis function and exponential.
I just asked because, I mean, for the hydrogen problem, the best basis is the eigenbasis.
Of course.
We know it, of course. So then I wonder, I mean, depending on your problem, a different basis might be more suitable. So I was just curious whether, I mean, Gaussians are nice, but whether you have more options currently.
For the vibrational problem, I will implement the Lagrange basis function.
Okay.
But
I mean, some people use harmonic oscillator bases and so forth.
But
I just wonder whether you have plans or...
The selection of basis function is not is a job of the user, maybe. It depends on the system.
But, I mean, your program supports any input basis functions, or does it need to be defined? I mean, does it need to be defined by the user?
You can define the basis function, but the integration is numerical integration. Also, the computing cost is a little high, but you can define and define basis function and potential.
Okay. Okay. Thank you.
Thank you for the nice talk. This may be just partially related, but at the beginning you mentioned also other science cases like astrophysics, for example. That would be like in the first slide or something. That would
this one?
on the second other one.
Okay.
Like in nuclear astrophysics. Would the idea be to use the same few-body.jl also for the other use cases, or is this just, I don't know, for show us other possible few-body system?
Yeah, there are use cases of few-body systems in other fields, only for few-body systems. But of course, there is a use case in the nuclear physics and cold atom physics, and my former field, quantum chemistry. So,
And I guess also, like, if you do use this package to like compute some kind of scattering amplitude or something, it's also useful in like astrophysics and so on. Yeah. Any other questions? Nope. Thank you.
Thank you so much.
Yeah. And hope it works as well. And okay, it works.
Cool. And now for the next short talk.
Thanks. Okay. So thank you, and thank you for attending this mini symposium. I'm one of the organizers of this mini symposium, and I'm Akio Tomiya from Japan. And today I'd like to talk about the visualization of the lattice QCD. That's a kind of series talk of, how to say, by my collaborators. Okay, so this is kind of a repetition of the what my collaborator talked, but I repeat. So I'm interested in the quantum chromodynamics. So quantum chromodynamics is one of the fundamental theory inside the nuclei. So you know our how to say our body and also the all of the materials how to say constructed by atoms, and the atom is constructed by a nuclear and electron, and nuclear actually constructed by quarks and gluons, and that's described by one of our quantum field theory called quantum chromodynamics, and that is basically nothing but just quantum mechanics, but this is highly correlated and relativistic, so it is very difficult to solve. So we need something new too to, how to say, calculate. So that tool so-called lattice QCD. And so, okay, yes, let me move on. Okay, oops. So this is the actually vacuum of lattice QCD. Something, how to say, wiggling there, right? But this is actual quantum vacuum. So quantum vacuum is not empty. There is something. So something annihilate and create and annihilate, and again and again. So this is quantum fluctuation. And lattice QCD can handle this kind of quantum fluctuation. And I did some visualization of the quantum fields. Okay, so the quantum field theory, like a QCD, so typically QCD is a theory of the strong force. This is the one of the fundamental force in our universe. And strong force holds quarks inside the proton and neutrons, and it carries by interacting gluon fields. Even the lowest energy state contains a quantum fluctuation like that, and lattice QCD makes those fields numerically accessible. Okay, this is our formulation. So this has been formulated in more or less like 40 years ago. And, no, 50 years ago. And the equation on the top is a so-called QCD Lagrangian. And basically we, how to say, calculate this thing from first principle way. And we just discretize our space-time and we calculate all of possible quantum fluctuation. And quarks live on this grid. And we define the gluon field. This is basically similar to the electric or magnetic field. And defined on the link or bond, I would say. And we just calculate all of quantum fluctuations for quarks and gluons. And this is a schematic picture of our space-time. So we discretize the space-time, not only space, but the time as well. And this is a kind of three-dimensional version of our four-dimensional lattice. And this is why I made this kind of package. I made a package so-called visualizing LQCD. So this is my motivation. So first motivation is so for outreach. So as you can see that, you can kind of imagine like this is the quantum field, right? Without this kind of image, it is difficult to explain the idea. So this is very, how to say, it works. And also, it also works for the research meeting or conference. So by using this kind of figure, so I can explain very easily. So I can, how to say, I can give you my, how to say, ideas. And also, actually, there is a previous work done by also people in Australia, but this is has been done in 26 years ago, and also this is closed source, and I wanted to make a open source version of that. And the calculation is actually slightly hard, so as we explained. And our lattice sites are like 24 to the 3 times 32. That's really huge, right? And this is a 1.8 million 3 by 3 complex matrix. That's really hard. And I want to visualize this one in a, how to say, rigorous way. And so to visualize that, we need some theoretical technique, so-called smearing, that is a kind of smoothing. And by using that theoretical tools, that I can safely visualize the gauge configuration. And this is how it works. So by putting this kind of script, this is Julia, and so we have some universal file format, so-called ILDG, and by inputting this ILDG format configuration, we can visualize the gauge configuration. And we had several series of talks. First one done by Ho Xiao, that he explained about multi-GPU acceleration, and just before this talk, that Yuki Nagai and Kenta Yoshimura gave a talk on the some numerical detail of the lattice QCD calculation. And now I'm presenting about how to visualize it. So this is how to say sequence of the calculation. First, input file is a 4-dimensional configuration. This contains that 24 to the 3 times 32 lattice, and each bond contains a 3 by 3 complex matrix, very large file. And by fixing the temporal direction, so first I take a size for equal 1, and I make a plot. And so to make it some animation, so we just set the size for equal to 2, and then repeat the same procedure, and repeat it again. Then we get the, how to say, animation, what we have seen in beginning of this talk. So, and we have 2 visualization for, how to say, 2 operators, I would say. And so first, this on the left is that visualization of local action density. This is intuitively, this is, how to say, intensity of the energy. So the white part is a very, how to say, energetic gluons. On the right is a topological charge density. This is intuitively, this is, how to say, where the gluons are very topologically non-trivial. And again, this is a usage, and what you have input is that how they specify the observable and the renderer and the threshold policy, because that how to say the energy is continuous variable. To make a surface, we need a threshold, and the slice sequence, and camera motion, and how to say the color of the back of that image. And then this is a workflow, and first input is that so ILDG treated by a gauge field gel, and we calculate the energy density by Wilson loops.gel and gauge fields. And the calculation done typically in the gauge field.gl and render by GL Marquier. And finally, the output is MP4. This is nothing but just a video file. And so calculation takes time, but we can, get the visualized version like within 15 minutes. So this is not so bad. Okay, so this is the end of my talk. So I made a package for visualization of the very abstract four-dimensional lattice QCD. And I succeeded to make this package thanks to the codecs. And finally, we got, this kind of cool visualization as in the previous works. Okay, thank you very much.
Any questions? One question.
Yeah, thank you very much for the nice talk. So far, as far as I understood, it's only about visualizing the vacuum, right?
Yeah.
Are there any plans to extend it to, I don't know, some particle fields, for example?
Yeah, in principle, I can extend the, so theoretically, just insert some operator to the system, but that corresponds to the putting a particle in the system. That can be done, but I haven't. Maybe next step.
Okay, thank you.
Thanks.
Any other questions? Nope. Let's thank the speaker again.
Hello? Is the sound? Too loud?
Yeah, it's working.
Hello? Can you hear me? Cool. I'm going to talk about my package, ray trace heat transfer, which I also presented in Eindhoven. What?
Just one more minute.
Okay. Oh. Sorry. Okay. Yeah, I'm going to present this package. I also presented it in Eindhoven 2 years ago, but there's a lot has happened since. My name is Nikolai. I'm an independent researcher. And first I want to talk about what does the package solve. It solves the radiative transfer equation, and that's basically an energy balance along a line of sight where radiation can be scattered away, it can be scattered into the pencil, it can be absorbed, it can be emitted and transmitted through. And that's basically true for any direction in this room, for example, and any point. So it couples the entire room, for example, right now. It has 7 degrees of freedom. It has three positional, 2 angular, and wavelength and time. So it is quite complex to solve. And then I just want to show one of the slides I had in 2024, where I listed a lot of things that I wanted to work on. And I can just show that how far I've gotten this far. Actually, on the same day of my presentation, I had a breakthrough afterwards in designing a new matrix scatter reflection method. Then I've also included 3D domains. I've tested GPU, and I haven't had success with that, so that's not included. Then I've developed spectral algorithms also basically for the colors, so to say, but it's based on thermal radiation. Then I've included non-uniform gas properties. I have not solved time-dependent problems because in engineering it's mostly steady state instantly, because light is so fast compared to the length scales we're working with. And then I've also worked with large matrices with memory limitations. Just to show how it works in 2D. For example, here I've defined 16 triangles. Then I put boundary conditions onto the superstructures, and then I mesh it, and then the sub-elements basically inherit the superstructure boundary conditions, so that you don't have to put it on every small piece. Then afterwards I do some ray tracing, and the ray tracing, it's different from the ray tracing that many people know from rendering, because in rendering you have like a place where you're viewing the domain from, and you're basically only interested in the rays that hit that for example, my glasses in this room. But in this case, you have to know everywhere, if I emit a ray here, what's the probability of ending up everywhere? So you end up with an exchange factor matrix that describe all of those probabilities for the entire domain. And then after that, I do smoothing to enforce energy conservation and reciprocity. And that increases the accuracy of the calculation. And finally, I solve for the heat transfer for the entire domain in a linear system. And the heat transfer, it's based on the exchange factor matrices. And the smoothing, as you can see here, the top one, it's very noisy because it's based on ray tracing directly. And the lower one it's been smoothed. And yeah, the smoothing, it's a topic in itself. And I have a paper upcoming about it. Then there's a spectral, I developed a spectral solver too. That's, you know, the extra dimension in the wavelength. So it's basically, you have one problem then if you have the spectrum, then you suddenly have like 100 of those problems that are coupled through things like the temperature. I found out that I set up a solver basically, and then I found out it had a special Woodbury matrix structure with a low rank, so it could be made a lot faster. Now it has linear complexity compared to how many wavelengths you add. And then I was also able to, with some help from AI, to also derive the analytical Jacobian of the entire map. So now it can solve also for very high optical depths, where the original algorithm had a very slow rate of convergence. And it reproduces here the plot. It's an atmosphere that gets thinner and thinner in the height, and it's transparent in the visible spectrum. And then when the light hits, it can't get out because it's opaque in the infrared spectrum. Then I also have developed a 3D solver. Here I have one hot end and one cold end, and you get the gradient across. Yeah. Then I also, as I mentioned, I used it to solve large-scale problems. For example, this problem is a 1,000 times 1,000 geometry. That means there's 1,000,000 elements. That means the exchange factor matrix will be 1,000,000 times 1,000,000. Of course, you can't store that, but you can do it sparsely. And then trace 1 billion rays, and ray trace smooth and solve. It took less than 5 minutes on my desktop. And as you can see, the smoothing, as I mentioned, is something I've developed that's coming in a paper on archive soon. It reduces the error from the blue scatter onto the orange right on top of the analytical solution. Yeah, that was basically it. That's all I had.
Thank you. Any questions? I think I have one. You talked about low-rank approximations or low-rank structures.
Yeah.
Can you talk a bit more about what kind of low-rank structures? Or
Yeah, I can show you the matrix. You can't. But it's basically, if you have the basic algorithm I developed for the spectral, it's where you have, it's a least square system, where the top blocks, that they couple the entire system, and then you have like a diagonal underneath, and that means you can basically simplify it a lot and get it much. I mean, the way I set it up originally, the complexity was square in the spectral bins, but now it's linear. So,
okay.
Yeah.
Okay, yeah, I see. Thanks.
Thank you.
Any other questions? Nope. Thank you so much.
Thank you.
attending, and we have photo session at this. So in 5 minutes. So okay, in front of this stairs. So so we have to go. Thank you for attending.